Just want to say hello and welcome to everybody. So I'm Professor Liz Bentley, I'm Chief Executive at the Royal Meteorological Society. I'm absolutely delighted to be at one of our face-to-face meetings, getting back into kind of the real world again, and wanted to welcome you all here to ECMWF, and also to thank ECMWF for hosting this meeting today, and particularly to Mark at the front for all his input in getting the meeting together. This came from a discussion, so Mark sits on the Royal Met Society's meetings committee. It came from a discussion probably 2 or 3 years ago now, prior to COVID, about a meeting that was held in 2006, looking at seasonal forecasting and the use in the energy sector. And it was felt that it was right now to come back and revisit this topic. 15 years, it is now obviously on from that, to have a kind of a look at the impact and the use of seasonal forecasting in the utility sector. So that's where the idea came from, and this meeting that took place in 2006, I think it's probably people in the audience who even participated in that meeting, so you will remember that, I'm sure. So I've just got a few slides before I hand over to Alberto, who's going to kind of launch, I guess, the meeting and chair this after, or chair the first bit of the session. So I'll take you through some slides, just a few admin slides from the Society. So just to let you know, we are recording the meeting. It's not being live streamed out, but we're recording it, and it'll be shared online after the event. You've hopefully picked up a programme and are aware of the programme, but here it is anyway for you. So we've split the afternoon into 3 sessions, and in between session 1 and session 2, we've got a refreshment break. So tea and coffee available just outside the lecture theatre here, not downstairs where you arrived for the registration. Hoping to close the meeting with a panel session, so there'll be an opportunity to ask questions after each talk, but also to hold maybe a discussion with questions right at the end of this afternoon as well. I'm told, I think on the back of your badge, there's a bit more information about emergency and where to go and who to follow. So I'll leave you to read that in your time. But I'm told that there are no fire drills expected this afternoon. So if you hear anything, it's for real and we need to exit the building. We have fire exits at different parts of the usual kind of air hostess directions, and as I say, there's some information in your name badge that will hopefully give you directions of where we're going to congregate. I think there's also information on there about first aid, but if you need any first aid, just contact either any members of the Royal Met Society team. We've got Catherine, Hannah and Hayley somewhere, and you'll see them roaming with mics as well when we're asking questions, or Mark, I guess, is the other person to contact if there's any first aid needs. A couple of slides just to promote some work of the Royal Met Society. So just wanted to point you to Met Matters. This is something that we launched last year. So kind of our public outreach arm of the Royal Meteorological Society. Lots of interesting content pitched to the general public audience, and obviously covers some of the topics that we're talking about here today. And also, I'd be told off if I didn't try and promote the membership of the Royal Met Society. So we're a membership organisation. I'm sure many of you here are members already, but if not, if you're interested in finding out more, there's a website link on this slide, or just come and have a chat with me and I can try and sell you a bit of membership this afternoon. So I'll close there. I'm going to hand over to Alberto, who's going to take us through the proceedings to start the afternoon. Thank you.
Start to talk. Just swapping slides. Hello, everybody. Don't know if it was mentioned, but we are recording. So hi to those of you who are listening to us from the comfort of your chair at home. And hello to all of you here. It's Control. So it's a pleasure to be here to launch scientifically, after the nice introduction from Liz, about the scientific advances of seasonal forecast in utility sector. So we're touching on energy and water. And this meeting is based on a previous meeting. It was also done virtually about a year ago. Some of the speakers are here again. And we were trying to delay and see when we could have done this physically. So now is the time. First meeting after COVID for me. So that's great. So I'll give you a bit of a short introduction to launch the meeting, a few slides, a little more than few, but just to understand where we are working, in which space. Energy meteorology, in this case, it's valid for water as well. I work mainly on energy, so there is a bit of a bias, sorry, Ian. But it's the same for water and other sectors. They are inseparable at different levels. So basically what it means is that these sectors really require meteorological information, weather and climate, for different type of activities, starting from assessments using the historical data, and then for the forecasting, short-term forecasting for solar power. When there are big drop of solar power, you want to anticipate that. Hurricanes for operations at sea. Here it says oil, but it's I think it was meant to be wind offshore, and then El Nino. So interannual variability for changes in demand and long-term changes for planning years ahead. Here in this meeting, we are focusing the middle part, so kind of hurricanes, El Nino timescales, so from weeks to months. So that's our focus. And in particular, if we look at what meteorology, how we can map weather and climate into the utility sectors, as I said, in many sectors, this is how we reflect the use of weather and climate for those sectors. So for historical climate, is about planning and finance. For the future, in terms of forecast, we have a short-term forecast used mainly for operations, monthly forecast for maintenance, and seasonal forecast for management of resources, and climate projections for investment planning. And again, we are here in between maintenance and management, that's where we're talking about. But there's many other applications, as you would know, in all the other areas. Very interesting, but little time to cover them here. Okay, so the meeting is based on a project that finished about 6 months ago, a European project, almost for a year long, called SECLI-FIRM, which was about assessing the added value of using seasonal climate forecast for decision making. That's the long version of SECLI-FIRM. And the way it started was through some curiosity from someone from the energy sector, and more than curiosity was the fact that some events were really hitting their bottom line. So particularly, you can see the spike here in the middle graph at the bottom. It's a spike of electricity prices that were linked to a heat wave, which is mapped on the left-hand side, and that heat wave was not anticipated. So the question is, can we anticipate that and try to mitigate the effect of the price spike? Not to reduce it completely, but do something about it. So that's how SECLI-FIRM concept started. We put together the proposal. We went through a couple of iterations, and then we did the work. I'm not going to talk much about the work because a lot of the discussions and presentations today about taking from SECLI-FIRM. I just show this result just to show you that there was real science used, although I'm not presenting any science here. So the graphs there represent the science, represent the seasonal forecast and the way they were used in terms of temperature forecast, precipitation, even wind speed, and in some cases solar radiation, and mapped onto the energy needs, in this case for one case study, which is about the heat wave event in Italy, which I showed before. And then we ended up with the delivery. So it wasn't just about the science. In fact, the science was a little, one component, but it was about the delivery and how we use this science. So the delivery in the end took different shapes. There's an example here on the left, which is a graphical view, but more ad hoc and a way, something that can be created more kind of flexibly in a way. And on the right-hand side is more a visualization tool, which is at this stage is automated. I'll show you in a minute. what we found that is the exact way in which the climate service is delivered is not critical, but the visualization tool often helps because it focus minds in terms of what you're seeing and so on. So even if the ultimate final delivery is not done through the visualization, it's always helpful. Of course, we need to also be careful not to try to build too many visualization tools has been done in European projects. Most of them, in the end up in the tool graveyard, unfortunately. So that's something that we need to keep in mind, that the sustainability of all these efforts we do. And here is one of the results. So fortunately, in our case, we were quite lucky because we were able to continue the collaboration. We are still continuing, and I'm just showing something quickly here to demonstrate how we're using seasonal forecast for an operational system, which includes visualization and data delivery. And it's based on a tool that we developed under C3S initially, and then it was further developed under SECLI-FIRM and in a co-development fashion. So if you want to learn more, there's also a very free tool version of this tool, which is called Teal, and Teal is not an acronym. It's a name, an English word, and I can explain why we chose Teal. But have a play, free version, if you want to learn more, on the website here. The other aspect I want to touch on, very important in the service production. 10 years ago, 15 years ago, like when it was 2006, well, actually 16, 17 years ago, was the main focus was on the science, not so much on the delivery or how it was used. We moved away quite a lot from there in this sense. The science hasn't progressed as we would have expected, but the engagement has, and that's a key step in the co-creation of climate services. And so with this slide, I just want to emphasize the fact that the engagement with users is key in the development of the climate services. And in the end, the main aspect is really communication. I mean, there's a lot to talk about co-design, co-development, co-production. There's all this world with co, and so it's a way to keep your mouth full. But in the end, it's really communicating. You know, it's just talking with the people who are going to use, get their feedback as soon as possible, in order that you don't go too far, as traditionally we did from the science perspective. You know, building all sorts of tools that we think everybody's going to use, and then they go onto the graveyard I mentioned. So I should mention also SECLI. We're focusing here on SECLI-FIRM because I was coordinating that, but I should acknowledge also the contribution of many other climate services from Europe particularly. There were about 25 projects between H2020 and ERACCESS. I won't explain the acronyms, but you know, just remember about 25 projects, so different sectors, different aspects and so on, but all contributing to climate services. So there's a lot of information that is being created, and some of that is going into this project that where we're contributing with our organization WEMC, Focus Africa. In fact, I just came back from Tanzania. Here we're working with Southern Africa, and we had a great meeting there, great collaboration. So I just want to acknowledge them and say hi, team in Tanzania, for your hospitality and the great work doing to try to develop climate services there, based again on case studies like we did in SECLI-FIRM. I didn't explain, but basically we are looking at different countries, different sectors, combination of so there is a real focus on end users, and that's I think it's working out very well. And in 2 weeks we also have a stakeholder workshop. It's a bit far, but there's still time to go if you're interested. It's going to be in Pretoria. Just to get to concluding remarks, as I said, for the climate services, science is key. We still need to work on the science, of course. We need to develop and improve the models, particularly for seasonal forecast, which is the trickiest one, I would say. But in terms of service development, we should often or maybe always do that in collaboration with users. So avoid getting into the trap of staying in your office, think that you cook up the best tool in the world and then find out that nobody really needs it. And sometimes, and often actually, the solution is much simpler than you think. And because people who are using this, they are not knowledgeable about the science. And so they want to start from an easy place, something that they can understand. And that's where, you know, the difficulty comes. Sometimes you go too far, whereas you need to step back and start the conversation from early childhood, almost. If you want to learn more, there is a book on weather and climate services for the energy industry we wrote a few years ago. And the beauty of this, apart from what's inside, is that it's free. So you can go and download it, open access, and enjoy the meeting. I'll now give the floor to Shanti, who used to work at National Grid. And is a great promoter of use of climate and the energy sector when he was a National Grid and continues to do in his role now at the Royal Met Soc, and is also a representative of the Royal Met Soc at the European Met Society. So quite important roles, and it's a pleasure to invite you here to chair the next session. Thank you, Shanti.
Thank you, Alberto. Sorry.
Yeah, you go.
Hello, can you all hear me? Yeah. Can I just welcome you and add what Liz and Alberto says? Welcome to this first face-to-face meeting. And I'm looking forward to hearing some of the presentations this afternoon. And as Alberto said, that my experience or my background comes from the energy sector as well as climate change and adaptation. The other key factor that Alberto brought out is 15, 16 years ago, we were looking at the science. Now we're looking at how the science can be applied in practical terms. And hence, I think we're so fortunate that we got speakers here who are actually talking about science as well as the practicing users of seasonal forecasting. So in my section, the first speaker is Anna Broadshaw. Now, Anna works at the ECMWF, and I'm sure many of you know Anna comes with a wealth of experience on the seasonal forecasting side. She's also leading a team at the ECMWF on the Copernicus project. She has huge amount of experience on the long-range forecasting. And in doing that, I think she has been collaborating with so many people around the world as well. So I think we are so fortunate to start this session with Enka. And before she came to ECMWF, Enka worked at Hadley Center, the Met Office. So can I just welcome Enka to just deliver the first presentation? And as Liz says, presentation about 20-25 minutes. There is a time for questions. And if there are more questions, we can take those questions in the panel session after tea break. Thank you.
Thank you. Wow. I'm sure this is almost unnecessary. It's nice to see you all here, although I'm a bit surprised at the composition of the audience. You will find what I have to say in the next few minutes rather simple. But I thought, encouraged by Mark, I thought I would take the opportunity to set the scene about the basis of seasonal forecast, long-range forecast more generally, ensemble forecast more generally, and how we go about evaluating them. You will not find the answer to the question of which is best, how good something is in absolute terms here, but hopefully you will leave with some understanding as to the angles from which somebody needs to analyze such data in order to understand how much use they can make of it. So I will very quickly go through the setting of the scene and introduction of the terminology, so you make sure we're on the same page. I'm sure the presentations that will follow me will use some of these terms. Then I will talk a bit about the evaluation and the angles which we adopt here, and then give some examples from the Copernicus Climate Change Service. To save some time, so you all know that the basis for long-range prediction rests on the slow varying components of the Earth system which affect the atmosphere, lending predictability. You either measure them and you assume they stay relatively constant, in which case you know their state, or you can predict the evolution in time. The further you can predict their evolution, the further your predictability of their influence on the atmosphere will be. Such components will need to be measured. Their evolution and the interaction with the atmosphere, in particular the troposphere, need to be modeled. You've all come across methods, empirical methods, which use relationships derived from historical records, in which large-scale features typically are related to local conditions. Dynamical methods, we refer to those very much these days in this way, but in essence, they involve models of the climate system, of the Earth system in general, describing dynamics, describing physics, and use these models to predict the time evolution from some measured initial conditions. There's also increasingly, and there have always been actually, hybrid methods in which you use the models for something and then you might step further into the application domains, into the local effects using empirical relationships. I'm going to be talking only about models for a minute, or in a minute. Again, the models do resolve the equations that describe the fundamental laws of physics. So it's not simply a linear relationship, it's not a statistical correlation, it's more fundamental than that. And we use numerical methods to approximate the solution to these equations because they do not have exact solutions. So because of this, we need to do some discretization, which would involve and will incur some uncertainties and some approximations. Also, we need to create initial conditions. So we need to prescribe for these models which describe the world, the Earth system as a grid, in effect, to create initial conditions for all the points in this grid. So even if you just think about how many observations there are, you'll realize that it's not easy to create a gridded version of the world with uniform quality, so to speak. So the initial conditions will be another source of imperfection. In fact, models are imperfect and the representation of initial conditions is as well. So you expect errors, and typically we expect the errors to grow as the forecast range increases. Now, some errors are systematic, and probably this is part of the saving grace, which means that we can have a go at trying to quantify this systematic behavior and correct the forecast by post-processing. It's not to say that we don't want to improve the models, and when Alberto said the science hasn't moved much, I agree, but I also think that the chances of improving models on that kind of timescale of a project were never very good. But the ways in which you do the post-processing, you try to extract the information that exists in these model simulations, even though the models are not perfect, has progressed. And I think the project we mentioned has contributed significantly to this. To do this post-processing and to be able to understand the systematic behavior, we use what we call retrospective forecasts. You'll hear them referred to as reforecasts or hindcasts. I just wanted to put it on from the beginning on the board that they're the same thing in this respect. So then, because we do this for past periods for which you already have observations, we don't use the observations in this exercise. We do the forecast as we would if we were doing it in real time. We use the same models that we intend to use in real times and the same setup as far as possible. So then we can compare these retrospective forecasts to the observations and determine how far the model output is from the real world, so to speak. So the conclusions from this evaluation then can be used to either inform the trust in the forecast or to provide quantitative corrections. We use ensembles to account for the effect of the uncertainties that I hinted at earlier. So these are forecasts initialized using several sets of initial conditions. The outcomes of these forecasts is considered in this particular framework as equally likely. The idea is to represent the effect of uncertainty initial state. So probabilities now can be estimated for the different outcomes predicted because you have several realization. At long range, we use ensembles both real-time forecasts and hindcasts, so the evaluation has to be appropriate for ensemble outputs, for probability forecasts, for distributions of outcomes. The first step that we go to in the evaluation of models and their outputs is to estimate biases. So are the data from the model integration exchangeable with observations? That's to say, do they belong in the same kind of universe? Can I read the forecasts that come out of the model as things to apply in the real world? Typically, when we look to diagnose biases, and I'm simplifying things a lot here, we look at means and standard deviations of climatology of models, and we compare the models with some truth. Usually, we'd like to do it observations more likely than not, though we use some gridded products which include observations, but maybe more than that. So reanalysis are typically used. Apologies for this. I thought I've had some labels on my plots and I forgot to animate them. So ignore those two words for a moment. So I just wanted to illustrate for those who've not thought of this before, what I mean by bias. So here is a set of simulations. This is an index that forecast initialized in May. The first, these are monthly means. So we have 6 monthly means here: June, July, August, September, October, November. These are individual forecasts initialized ensembles each year in a number of years. And now the years are 1993 to 2016. It's really not important here what this is. But this is what, if you start to plot all the integrations you've done in the hindcast mode for this particular index, this is what you end up with. The mean of these realizations is this. We call this the model climate, or the model climatology, the mean climate of the model. You can do the same with observations. So the years I mentioned, 1993 to 2016, you can take the observations for this index and calculate the same thing. Well, these are the black lines. The thin ones are the individual values for the individual years. And the black line indicates the mean over that period. So in each point, you have the 24 odd numbers averaged. They are different. There is a distance between what the model mean is and the observed world mean is. Now, I know this, and you can probably see from looking here that compared to the observations, the model tends to be always colder. Can I use this for my interpretation of a real-time forecast? Here's a real-time forecast, an ensemble forecast, a number of realizations in the green lines. If I were to not know about the model climate, I would think, well, most of these ensemble members are below the observed climatology. This is an index of sea surface temperatures from the tropical Pacific, equatorial Pacific. So this would be indicative of La Nina. As you can see, by the end of the forecast period, you've got almost, well, half a degree at least of anomaly in the ensemble mean, if we were to mean the green lines. But remembering that these are elements that come from a model, and remembering that the model's average behavior, it's not a black line, it's a red line. In reality, by doing this adjustment, just compare from each ensemble member, you subtract the difference between these two lines. You end up with this as a forecast. So these are anomalies. And in fact, this indicates the opposite of what I might have thought if I hadn't thought about the model climate. So this is the essence of using anomalies, of doing bias correction, and of interpreting data from models that have been run for a long time. Typically, in weather forecasting, we don't do this. We can trust, because at the beginning of the forecast, even here, you can see the differences are not very large. But as you go into the future, these differences grow. So again, apologies is very simple, but I used to find it quite compelling. Here is a more precise example that relates to same thing, that relates to the way in which we process the data to create our example products. And I must stress the word example, because we don't claim to do some authoritative products best for everybody. Such a thing doesn't exist, I would argue. As we'll see in a minute, different sectors have adapted the model output in different ways to serve their purposes. But again, here on the left-hand side, you have the model climate. We marked on it the terciles of this. So these are the values that leave 1/3 of the data between the two and outside. So this is you know what percentiles of a data set are. From the model climatology on the left. And then we have a forecast. As I said, when I have forecasts, I don't deal with the real world for quite a while. So when new forecast comes in, it's the points in the middle, and then it's probably about 25 ensemble members. And then I can count how many ensemble members exceed the upper tercile, how many are below the lower tercile, how many are in between, and calculate the percentage of the outcome being in one of these three categories. And this is the thing that I take from the model and I then transpose in the real world. What I leave the room with is to think that the outcome will be is 25% probability of being above the upper tercile, 8% probability of being below, and the rest in between. But then when I give this to a user, I invite them to interpret this in relation to the climatology of the real world, in which now the terciles have very different values. So, and sometimes, quite often, may have different distance between them that there are in the model. So this is the forecast message that gets transferred and extracted from the model and transferred into the real world. I won't dwell on that, but I want to bring one more thing to the fore, and that is the issues with biases. So you might think that, well, at the beginning of the forecast is no big deal, I may just ignore it. It's not wise all the time. So here I'm looking at 2-meter temperature in 2 regions which are marked on a map, and this is the full annual cycle. These are daily data based on daily data. It's not a single realization of daily data. The sample that is averaged in these colors is 25 times 23 realizations. And as you can see, there's a lot of noise still in spite of this, this very large number of elements in the sample. And depending on which time of year you're looking at, the behavior of the bias is very different. So you have times when it's pretty much close to zero. You could argue, do I do more harm or more good by correcting this bias? But there's other times of the year when things clearly do something strange. And they do something strange within the first 3 or 4 days of the forecast. So each of these steps on the x-axis is another day. This is for the southern US box. It's an average over a whole box, so you might get worried because this is not just a single point. It's quite a robust and a large area. In that area, there will be points at which the jump is even bigger. If you then look at a box over continental Asia, you will see a similar behavior. In the summer months, this is August. I can barely see it myself. Here's August. So you can see that the sort of positive biases, this is what we refer to as bias, by the way. The positive biases are of the same sign for the 2 regions in summer. And in winter, over the region of China, the bias is considerable, but it's negative. Now, we use this kind of information sometimes to try and understand what's going on with the model, because this, for example, could hint at problems with the representation of the land surface, given how quickly the bias develops into the forecast. This is just one model. Here's another. So whilst the precise magnitude by which models are in error in this sense differs, many times the errors can be common. And genuinely, you could learn quite a bit from this. More importantly, you can probably spot from here, whereas here initializations are once a month. In the bottom row, the initialization is about once a week. So there's more bunches of line or more lines because the initialization is more frequent. But what I wanted to point out is that in these areas, really, you cannot trust the model, the data coming out of the model as is. In these areas, I'm not sure what bias correction would actually achieve, given how noisy this is. Okay, quickly to multi-models or multi-systems, as I tend to refer to. As I said, models are not perfect. They are differently wrong sometimes, or they are commonly wrong other times. In order to try to quantify somehow the effect of of errors and uncertainties coming from model formulation, we tend to put outputs from models together. It's not the most sophisticated way of doing it, but it is effective because several centers run their own forecasts and then you can just bunch them together. And this is what the Copernicus climate change does. Here's an example about how different forecasts coming from different centers. You've got the colors representing forecasts from a number of centers, and you can see this index, the time series for this index, you can probably just about glean one model prefers this part, another prefers this part. So you do increase not just the spread, but probably increase the sort of increase the coverage of the possible outcomes. And if something is really not capturing a particular process, one model, another might be capturing it and compensating for it. Does this increase the spread to amounts, to magnitudes, to values that are that render the forecast unusable? Well, in some cases it might. The question is, what do you care about when you look at these forecasts? So just very briefly, I'll come back to this later. The seasonal forecast, multi-system at C3S, and maybe I should clarify now why I'm talking about multi-system. As I said before, a forecast system is a combination of a model with initial conditions and with a method to generate ensembles. In the case of C3S, we do not prescribe any of these things. Everybody does it the way they do it in their operational activities. Therefore, everybody brings a new system. Arguably, a multi-model will be a place where you have several models, but you do the other bits the same way. Regardless, we use 8 contributors to this combination, and we get a lot of data from them. We collect a large set of variables. We share this large set of variables through our technical interface. This is the list of variables. We offer documentation to explain the structure of the data, to give instructions about how to download. There are forms to download. There is download via API. There is user support. The data is at monthly, daily, or even sub-daily frequency, and it's all available for free for everybody to use for every purpose. We do create, in addition to publishing a catalog with a variety of data, we do create a set of graphical illustration of products that are obtained by some processing that is similar to the description I made before. Now I'm going to move straight to forecast quality and how we might want to go about evaluating it. So I didn't necessarily want to call it verification because it's quite ambiguous what we mean by this when we have forecasts expressed as probabilities and ensembles. So trying to think about this is a very simple set of steps through the idea of forecast verification. Firstly, you need to worry about why you want to do this. You want to know how accurate the forecasts are, but the accuracy of a forecast doesn't have an absolute scale. If they were perfect, maybe that would be good enough, but they're not. And then anything less than perfect, is it any good or not? So there is another angle, which is, does it enable the user to make better decisions than they would have without this information? You might want to do that to compare different contributions, different sources of information. You might want to monitor by checking how the forecast behaves and its performance changes over time. Or you might want to do this bias removal and interpretation of the data. So all of these things come under the purpose, the umbrella of verification. Now, because we're dealing with ensembles and probabilities, we need a large number of events and a large number of forecasts to try to establish the average behavior, or indeed even the individual behavior if you want. But because a probability forecast cannot be judged as correct or incorrect just on a single event, that is absolutely necessary. And because of that, because we deal with ensembles, accuracy is not the only thing. There are other attributes of forecast quality that we need to look into. And these 5 that I've listed here, I will just very briefly describe for you. So this is just by way of explaining what kind of angles you might want to take in evaluating a forecast. So in terms of accuracy, that's clearly about the correspondence between forecasts and observations, whereas skill is a relative measure, which shows whether a particular method is better than another. A method of reference, which you can pick either based on your particular practices or just more general, either a naive forecast, I would call it. Either you take a random prediction, or you take a persistence from the previous period, or you take climatological averages. Regardless, a skill score is calculated with a formula like this. In effect, you calculate how much better the score of your method is than the same score of a reference method. Reliability tells you whether the probabilities that you issue are unbiased. So let's say that you issued a forecast of 80% probability of rain. If of the times you issued that forecast, it rains every time, your probabilities were wrong. probability should have been 100%. So in all situations in which you have issued 80% probability of rain, a reliable forecast would only be right 80% of the time. Reliability is a property that can be improved by calibration, but it's a property which is important to pay attention to, because if you use the probabilities in a quantitative way, you do not want them to be wrong in that sense. A resolution of discrimination, I won't go much into it, but if you have a look at the slides, you will see it there. It's about the opposite of reliability. It's about, now, can I distinguish between event and non-event? Or can I distinguish between a forecast with high probability or low probability? They are similar. They are, one starts from the forecast probabilities. The other one starts from the observation. But in essence, this picture probably summarizes it. Good discrimination is when the forecast and the for events and non-events looks very different in distribution sense. Doesn't have good discrimination if the model always predicts a distribution that is roughly in the same place, regardless of its event or no event. Lastly, sharpness. This is a probability of the forecast and not much to do with verification by comparing with observations. However, this is something that users that I've come across tend to value, forecasts that give very clear probabilities. Probabilities close to 0 or 100%. And you can easily imagine why somebody would want a confident forecast. However, whilst desirable, these are not useful if the forecasts are, if the probabilities you set are wrong. Right, enough with the theory. Let me give you some examples from practice. So the C3S seasonal website and service more generally creates some example products, as I said. Here are the graphical products. You can find these on the website. You can examine them. As you can see, they target about 7 variables, and they come as maps or time series. So I'm going to show you a couple of examples of scores and verification that we've done for some of these. So these are the only variables for which we've even attempted to do any verification. And in particular, we do the verification or calculate scores for the products the way we calculate them on these pages. So it's not, verification is not something that exists in a vacuum. It needs the context. It needs your definition of the product. You can score very badly with a very good system by just creating a product wrongly. Okay, this is just the maps that you can navigate. You can easily find them. So here's an example. This is the ranked probability skill score. Is a skill score, so it compares the score for the forecast to the score for a reference. In this case, the reference is climatology. It is a error type score, so it looks at the distances between observations and predictions, and it does do some bias correction because it scores whether you hit the category in which you are predicting things to be or not. So here green is good. It means that your forecast method has better rank probability score than the reference, and green and red is bad. So you can see these are the models that we use, and you can see that they do in places better than climatology. For those who can see the details, you'll probably see that not many of those places are in Europe, but let's worry about that later. This is the multi-model combination. You can peer at this and have a look to see that the multi-model combination has a bit more green in places, has certainly less red next to the South Pole, which is good. But again, this is just a generic verification. I wouldn't recommend to anybody to take this product and try to apply it in a, I don't know, water management situation, let's say in the UK. You need to do much more bespoke evaluation. The same for precipitation. If you remember the colors on this map, the greens have gone by and large. They only remain in the tropics. Again, the multi-model is slightly better, but only marginally so. Atmospheric circulation, which you'll hear probably about in a minute a lot more. So here is the multi-model that we use in Copernicus, correlations this time to keep it simpler for winter and for summer. And again, if you look and spot the region of Europe, that is not anything to shout about. So the correlations can be negative. And even when they're positive, they're low. The situation isn't much improved in summer. And in fact, the driving of the local conditions by circulation in summer is probably slightly less strong. Probably my, if not my last, certainly my penultimate slide. So in order to summarize some of the information on atmospheric circulation, we did a diagnostic looking at the North Atlantic Oscillation. And in the plot in the top left-hand corner, we do have in blue the reality based on ECMWF Reanalysis. And in the dots, we have the values for these periods from the models. This is from the November forecast, I'm sure. And the averages over the 4 months period. The other line, the line that goes to the dots, which is green, is the mean of the points at each time point. And as you can see, the amplitude of the signal is not very is not similar to that of observation, and the correlation is quite low, is 0.34. So this is what we have to work with. In a table, I have put the correlation for the individual components of the system. So these are the correlations of the lines that you obtain if you join the dots with the same color, and some error bars on them. Now, as you can see, there are models which exceed the correlation of the multi-model in this particular definition, and there are models which are lower. But what I wanted to draw attention to here is the fact that this is one definition of the NIO. I put here a picture from a paper written by Laura Baker, which tests the hypothesis that the results aren't very different in principle, but in practice you can end up with very different numbers. So here we use the red boxes, the largest boxes. If you do the calculation with much smaller boxes, you end up with completely different value. In the case of one of these systems, the value has doubled. So this is why you need to really decide what it is that you want to work with, because if you took this and went away and thought this is the correlation for, or this is the score for the North Atlantic Oscillation, you will probably be misled. Thank you.
Right, we just got time for 1 or 2 questions. We can take them now. And anybody's got any questions? No. Okay, I think we got a panel session. So if you think of any other questions later.
Well, maybe I could, Shanti, I can ask a question if. So, well, I must say thank you. That was a really excellent discussion about the forecasting system and how it's built up. I really valued that myself. I guess at the end you're talking about the verification and the evaluation, and you were saying that the various users have their own kind of way of evaluating the forecast. I guess that's one of the key things that we want to get out of this meeting, promoting that dialogue. And there are ways in which the forecast system can be configured to help users, to make it better for users. So really a two-way dialogue is really important. Where is the value that the users gain from the forecast is very useful for us to know. So yeah, I just want to thank you.
But I would argue that whilst we value summarizing things in one number if possible, users might want to look at the series of events to break it down. So I'm doing here an average correlation over a period of time, but I might want to know whether the system could give me the right amplitude in a particular moment, or if in a particular set of circumstances. So there's a lot you can do by just looking at the set of hindcasts and comparing them with what happened, which is not captured in a single average number.
Thank you.
Thank you.
Bernd.
Sorry, another question.
Thanks, Anka. I've got one big question about what I would like to see more of. It would be the evaluation of real-time forecasts, because real-time forecasts are much bigger ensemble size, much better initialization compared to hindcasts, which are often much smaller ensemble sizes, and often in some cases even with a completely different forecasting system.
So I agree with you. I agree with you, although good practice and any operational, self-respecting operational center does use the same forecast system and strives to do the all components of the forecast system in a similar way. So for example, the initialization has to be consistent. I will say this much. I mean, the problem with the real-time forecast, there aren't many elements in a sample, so you don't get a chance to do this. That I think we could improve the methodology of understanding how well a single forecast has done. But I still think that probably the way forward is to increase the ensemble size of the reforecast of the hindcasts to match that of real-time forecast. And I know a center that's doing this. So the Bureau of Meteorology in Australia are building ensembles in the hindcasts equal to those in the forecast, so they can derive quantitative correction factors.
Thank you. Right, we can take up some more questions later if you caught any other discussions you want to take further. Our next speaker is Daniel Drew from National Grid. Daniel is the energy forecaster at National Grid. And prior to joining National Grid, Daniel has been a postdoc student at Reading University, doing various projects on energy predictions. And as Mark says, the real proof of the pudding on how this forecast is used is by the industry. So of the two industry people in this session, here's the first one, and see how they make use of seasonal forecast and what decisions they make. So Daniel, welcome.
Better, yeah. We have a forecasting team which runs 7 days a week, and our team is responsible for developing the tools that these guys use every day. And today I'm going to talk a little bit about our first attempts to use seasonal forecasts. So when I was brought in, my role was mainly to start to look at all of the processes that they run in National Grid and try to put the best weather data to those processes. I feel I should start with an overview of what National Grid ESO actually is. It's not quite as straightforward as people may think. So this is a pretty simple schematic of the energy system in the UK, electricity system. So once electricity is generated, we transmit it across the UK on the transmission network at high voltage to reduce the losses. It's then reduced in voltage when it gets into the distribution network, and then finally it goes to the consumer where the demand actually is. And we sit in the middle of this process about here. So we're moving the electricity to where it's needed and making sure the two sides of this are in balance. So making sure 24/7 there's enough generation to meet the demand. We're not responsible for the infrastructure of the pylons or the cables. We're just the system operator. So making sure the energy can get to where it's needed and there's enough of it, and the system is secure and safe. So if we lose one of the generators, if it trips or fails, that the system frequency still maintains stable at close to 50 hertz. So we're trying to do that as cheaply as possible. So why do we forecast? It's to make sure that this is in balance, to make sure that we have the correct amount of energy to provide for the end user. And we know how much reserve we need to hold. So if there is a loss or if there is a big forecast error, we've got enough generation to keep the system in a nice equilibrium. And of course, as we're responsible for making sure the flow can get to where it's needed, we need to model the flows on the network. So where is the generation? Where is the demand? Can the generation get to where it's needed? And we're trying to do this, and rightly so, because all of our costs end up on the bill payer. So we're trying to do this as cheaply as possible. So the earlier we can make decisions, the better for everybody. We publish all of our forecasts online, and other industry participants can then take a position based on what we forecast. What exactly do we forecast? We forecast both ends of this, the generation and the demand, and we do this over a range of spatial and temporal scales. On a spatial scale, it's really national level, right down to sort of regions which are defined by the topography of the electricity grid. So the smallest is about sort of 10 kilometers by 10 kilometers, so not particularly high resolution. And on the temporal scale, we're doing minute the next few minute forecasts right out to 2050, so 30-year ahead forecasts. So there's a full range of spatial and temporal scales, and we're doing generation and demand. For today, we're just going to focus on the consumer demand, so the final bit here, and at a national level. This is getting increasingly more complicated. Well, both ends are getting more complicated, but in terms of the demand, what we actually see at the moment is generation being put within the demand. So small scale solar panels and wind farms and batteries. And we don't see any of this as generation. We just see this as the demand reducing. So our job is getting harder and harder. And much of what's going on is weather dependent. So solar PV and wind are affecting our final demand in ways that we hadn't seen sort of 10, 15 years ago. So as I say, I'm going to focus on the demand today, and these are the key variables that we use in our model for national demand. The one, obviously, I'm going to focus on the weather, but I just want to point out a few of the others because they are actually a lot more important than the weather terms. So a lot of them are sort of calendar based. So our electricity demand is very predictable in terms of day a week. So weekends are lower than weekdays. Mondays are very different to Wednesdays. And even though these patterns have changed slightly during these lockdown periods, they still maintain that Tuesday to Thursday have a similar pattern. Monday and Friday are different. And of course, we've got this embedded generation, which means we need to model solar and wind at the same time as the demand. The big one for what's going to affect the results that I present today is the COVID lockdowns, which led to a sort of at the strictest lockdown, we had a reduction in electricity of around 25% of what we'd normally expect for that time of year. And so any weather effects are completely lost in comparison with that variability. So for the analysis we did, we were sort of battling with variabilities from COVID lockdowns, which were much, much larger than anything we were trying to model. In terms of the weather variables, the big one for demand is temperature, which, as we'll see, is quite useful for the analysis we were doing. So this is really because heating and cooling in the UK is very temperature sensitive. There's also the lighting effect, which we model through a temperature and radiation term, which we call effective illumination. And wind speed has a slight effect, mainly in winter. And so we model demand with wind speed and a term called cooling power, CP, which I haven't written there. And that sort of dictates, for the same temperature, but different wind speeds, how people respond in terms of whether they put the heating on winter's evenings. So as I say, my first job was really to look at all of the different processes we do, right from in-day right out to 10, 20, even 30 years ahead, and look at the weather data we're using and seeing if we can make any improvements. So in real-time management, so we call that, so that's between the next few seconds and 14 days ahead, we're using a weather forecast, which we buy from a weather provider. We're going out to tender the weather forecast in the next few months. We're quite happy with all of the processes that go on in that time period. We get our weather forecast, we get a probabilistic weather forecast, and we apply our models, and we can then give a range of demand values for the next 14 days. And we can inform decisions about, is the network in a sufficient state to manage? Can we manage with particular outages? Have we got enough generation to meet demand? Can we allow a particular line to go out for maintenance and still cope? And then beyond 14 days, we have similar sort of processes, but we're looking at, are we prepared for the next season? So for winter, do we have enough generation to meet demand? For summer, we have the opposite issue. Demand's very low, and we have a load of conventional generation that has to run. So nuclear generation. Can we manage the system when we've got such little headroom to play with? And then as we go further, so we're looking at the plan of the network. So what generators have told us they're not going to be operating, what lines are going to be out. Is the situation manageable for all different types of weather? And we have this cutoff in our weather data at 14 days where we just switch to a climatology. I say we just switch, we do blend slightly, so there's no jump. But so this project was the first attempt at working around this red line, and can we move from our operational weather forecast, our 0 to 14 days, can we start to include the seasonal forecast into some of these processes we run in the 3 to 6 month and the sort of 3 to 4 week ahead timescale? So I'm going to focus on winter peak. So that's the highest electricity demand on a particular day in winter. So initially we used a climatology, a single value we had from the last 40 years of weather. I'll say this quietly, we use Mirror 2 Reanalysis. That is just a legacy thing that we're doing various projects looking at other Reanalysis products. So we got the full 40 years of history. Previously, we were just using a single mean value. We've now switched, so we sample that history, and we do 10, depending on what application we're using, thousands of scenarios sampled from that historical weather, and then we apply it through our demand model. And so this figure here on the right shows all of the grey lines are individual forecasts based on our historical weather, and the red is the median of all of those runs, and the blue is what we were previously using, which is just the normal weather, the mean of those 40 years. So you can see that by doing this sort of ensemble approach, we were able to give the planners a range of possible values now. So particularly over Christmas, this is important. How low could the demand go? So rather than just that solid blue line sort of here in December, we could give them an indication of what the lowest demand might be if the weather happened to be mild and calm. And the beauty of this data set is that we could have a coherent time series of wind and solar generation derived from the same weather. So we could combine all of this together in all of our models. An absolutely crucial point is that all of our models rely on sub-daily resolution weather data. We're really focused on the points in the day that cause us trouble, so the peaks in the day. And to get those accurately, so far, we've shown that we've had to use the sub-daily resolution weather data. We are looking at whether daily data is enough to still inform our peak demands, but really at the moment, we have to have ideally hourly data. So as part of the SECLI-FIRM project, which was mentioned earlier, we were working with the Met Office to see if we could incorporate the seasonal forecast into our peak demand forecasts. So we were taking variables of temperature, wind speed. We didn't need to use radiation because our peak demand in winter is always going to be when it's dark. So our PV in electricity, solar PV, is going to be 0. So we got the Met Office to provide us with the seasonal forecasts based on Glossy 5, and it was shown to have some skill of the variables that we were interested in. So crucially, temperature in winter for the seasonal mean. It couldn't give us the daily variability, which is ideally what we'd be after. This is the forecast made in November, and the absolutely crucial part of this, and this is coming back to Alberto's point of the communication, we didn't have to change any of our processes in National Grid. We were able to communicate to the Met Office exactly what the input data looked like to our models, and they could then make sure that they provided us a file which we could just slot in, and there were no changes required. And I think if we had to make internal changes, this project wouldn't have been so successful, because there's just so much inertia in our system to make changes to our models. This is completely experimental though. This is for winter forecast 2020-21, all offline, not part of our production system. And it didn't inform our winter outlook, which we publish in October, which tells the industry what we think the system's going to look like for the coming winter. So it didn't feed into that. It was all offline analysis. So the idea was to use the seasonal forecast to transform the distribution that we were sampling from. So we had our 40-year history that we had a nice technique to sample, create 10,000 winters. Could we shift that distribution based on the seasonal forecast? The forecasts we were provided, so this is winter 2021, remember, had a clear NAO positive signal. So our distribution for temperatures and wind speeds were shifted upwards, milder, potentially stormier conditions. So when we then run that through our modelling process, that actually meant that we would have reduced our forecast of peak demand for that winter by approximately 500 megawatts. As it actually turns out, if we'd run the climatology, the ensemble mean would have been pretty much spot on for that winter. And so that obviously led to challenges internally trying to sell this as a process, given that the first year we run it, the value that would have normally used would have been pretty much spot on. Yeah. But so any sort of help in coming up with metrics to show that, because we know, our team know that this is a long term, we need to run this every year, and in the end, it will be better than the climatology. The limitations of this process, there's no seasonal cycle in the DJF. The temperature and wind points were not synchronized, so we couldn't use the wind power that was coherent with the temperature. So there are things we need to improve, and we're currently working with the Met Office to do this. Our winter outlook is published in October, and obviously this is a forecast that's produced later than that. So that is again an obstacle. So it could just be that we use this to provide updates on our winter outlook. So to conclude, we've been looking for the first time at using seasonal forecasts in National Grid, particularly for national demand, which is very temperature sensitive. The example we used was for 2021, where all of our demand forecasts were heavily impacted by the uncertainty due to COVID lockdowns, and they were around sort of 3 to 4 gigawatts. The amount we moved the forecast based on the weather data was about 500 megawatts. So it's completely dwarfed by all of the other stuff that was going on. We're still working with the Met Office to see if we can improve this process and to address some of those limitations. This is ongoing work, it's all offline, and it currently doesn't feed into any of our winter outlooks. Ideally, this process would be used in our winter outlook, and we also do a summer outlook. If we had a seasonal forecast for June, July, August that had skill, we try and do a similar process for that period. Thanks.
I like to keep on time, and I'm quite happy to take one question. Go ahead.
Hi, Anthony, from Lake Street Consulting. So thank you very much for your presentation. And good that you're trying to use some of the weather data and doing a Monte Carlo simulation. But the one thing that strikes me is you're using historical data for the last 40 years, and yet I think most people would think that the historical data over the last 40 years wasn't necessarily representative of what we expect for the next 5 years, for example. So I think Alberto touched on the point that science hasn't necessarily evolved as much as we would have hoped over the last 16, 17 years. But are there ways that you could incorporate climate data and the changes in regimes and the changes in the length of the regime in your work so that we take into account something to do with climate change?
Yes, we would absolutely love to put a climate signal into our data. At the moment, I should have said that we do put a weighting into our Monte Carlo sampling, so we sampled a more recent history more heavily than so I can't remember how we did, but 1990 onwards is sampled more frequently than prior to that. But still, it's not ideal. Absolutely, it's not ideal. And we'd love data that would help us do that.
Thank you, Nadia. If you just bear with us, we can take up some other questions later.
Hi. It's really nice to be here. ECMWF and our METSOC doesn't really get much better than that in terms of where you want to present as a user of forecast services. So thank you for the. Nope. That's okay. Thanks for the opportunity. What I'd like to do is speak. Jess is speaking later, and she'll deal more with the science of what we were doing in this case study. But as Alberto said, this is one of the case studies of the SECLI-FIRM program. We were looking at the wind and wave conditions during shoulder months in the North Sea for energy logistics. We started this 4 years ago. Actually, prior to SECLI-FIRM, we were doing work with the Met Office. And at the time, it was fairly focused on offshore oil and gas operations. I'm now part of the offshore wind team, so I'm trying to apply the same sort of approaches in the offshore wind operations. So that's why we have both oil and gas and wind operations here. I'd like to thank Hannah Brown, Jess, Ed Steele from the UK Met Office, some really, really close collaboration, coming back to Alberto's point about end users and the science. We don't know enough about the science to drive these improvements, but we do know how things are used in the real world. So that's where we tried to contribute. Gertie, not here today, wishing her all the best, but KNMI case study 6 with Tenet was quite close in terms of what we were looking at, what they were looking at. So some good work went on there. And Nicholas from UEA gave us some input to the economics for the project. So in terms of context, what do we refer to as shoulder months? Well, normally April to September or May to August are the sort of fair weather and the operational periods that we look at. When we're talking about shoulder months, we're talking probably sort of February, March, April, August, September, October. So we're trying to use seasonal forecasts to improve our operability, improve our management of operations in that sort of shoulder of the winter and the autumn and the summer and spring. In basic terms, how do we plan our operations? Well, we talked already about hindcasts and climatology. That's one thing that we can do. We can be as basic. When I say we in the industry, you could be as basic as knowing that it's better in the in the summer than it is in the winter, and planning all your operations there. We try to be a little bit more refined in our planning, and we use climatology. So here at the top, we've got an exceedance distribution. For wind speed, we might do the same for wind speed and direction, wave height, wave period, depending on the operation that we're using. So we use 40-year hindcaster data, and we say what's the average conditions that we get for 10 meters per second wind speed, because that's my operational limit, and that gives us a graphic or a tabular representation of how successful we're likely to be if we plan an operation in April, May, June, July through the year. And generally that's what we do in varying levels of complexity, so just single parameter or multi-parameter exceedance type references. We then take that onto a weather windows type analysis where we use the same data set and we say, well, we've got an operation that lasts 4 days. We need to have wind speed less than 12 meters per second, wave height less than 2.5 meters. What's the amount of time that it should take for that 4-day operation that's interruptible at any time through the year? And that then becomes also more complex if we have currents or tides or daylight as part of the operation. So what I'm trying to say is that there's a range of simplicity or complexity that we have in planning our operations. And then when we get to execution of operations, we move into forecasts, typically deterministic forecasts, but more often also ensemble. But these are products that you'll be familiar with: table forecasts, graphical forecasts, wind speed, wave height. But there's a huge amount of uncertainty and other limitations in those, whether it's quality of the forecast, the parameters that you're looking at, the sensitivity of the operations. We try and use things like alpha factors, which apply a level of risk management to a forecast if it's a particularly sensitive operation. But generally, if it's somebody on a rig or a vessel that's making a decision, they will use a forecast and look at the next 3 days ahead. Because that's generally the forecast that we look at, the horizon that we would use with confidence. Obviously, as we move from winter into spring or autumn into winter, in the shoulder months, that variability becomes more significant, and that's when we get particular impact on accuracy of the forecasts that we see. And now, more often than not, we're getting forecast, we're getting competition. We pay for these forecasts. There's no regulatory framework that says you must have a forecast. We do it because we want to improve operational safety and reduce costs. But when you have things like windy, I've got an extract here. There are others, but visually they're very, very nice and people like using them. But it's not what we would recommend using for flying helicopters or using an SOV or a CTV. But we do see people using them. So that's what we do at the moment with forecasts. The benefit that we wanted to get from SECLI-FIRM was to see how we could use seasonal forecasting to improve, particularly in the shoulder months, and see whether we could bring in new tools. But it's already been mentioned, the communication of those tools and those changes in products is actually possibly more difficult to manage. Even when you change a website, you get people phoning you up saying what's happened to the website. So when we're trying to introduce new tools, that's a different level of conversation. Also, well, when we're looking at forecasts, when Shell's using a forecast, we're looking to use the resources that other people are using, whether it's Vattenfall, Ørsted, BP, or somebody else in the supply chain. We're all trying to use the same resources, whether it's for a long-term turbine installation campaign, whether it's an SOV doing maintenance on offshore turbines, or a walk-to-work vessel on southern North Sea gas platforms, or flying helicopters. We're all looking at the same limited pool for resources. So there's obviously a supply and demand issue there that drives the cost, and I'll come back to that in a second. And as I've said, we have a lack of ability generally with more than a week to plan our activities. For instance, a vessel like the one there, the SOV, could be £30,000 a day if you're looking at it, and there's very little demand. But then if the weather improves and demand increases, the same vessel with the same crew with the same capabilities could be £90,000 a day, pounds a day. So there's a huge supply and demand impact. So what we wanted to try and do also was look at whether or not we could improve our short-term forecasting to get an added advantage there. But there are also non-financial benefits of improved forecasts. So the human element, you don't want a crew of 120 people sitting on a vessel like that doing nothing for 2 weeks because you've got your forecasting wrong and your planning wrong. But there's also the climate context. Vessels like that burn a huge amount of fuel, and that's a lot of CO2 that you're pumping into the atmosphere if you're sitting doing nothing. So it's another benefit of improve forecasts. So where, as I said, we wanted to bring in end user experience into the SECLI-FIRM relationship with the Met Office and with TenneT on the other case study 6. So we looked at some case studies where we said, these are events that have happened in the past, recent past, that had an impact on us. Could we have improved our response to those events had we had improved seasonal forecasting? First one was the beast from the east. This caused us some huge problems in the southern North Sea, partly because of the prolonged cold period that we had. But also then we had the impact of the storm from the southwest, which exacerbated repairs to any of the damage or any of the downtime that had been caused by the extreme cold. We had, obviously there was a sudden stratospheric warming. We used that as an information that in the coming weeks we could have an impact at the surface. What was that going to be? But if we had a better improved seasonal forecast, then we probably could have done more. The second case study we looked at was a rig move in the autumn of 2018. We had a rig similar to the one in the middle picture here. It's a jack-up rig that was moving to a location in the central North Sea. We had quite a lot of downtime associated with that rig move because the forecasts were not sufficiently long in terms of horizon. And then the last one that we looked at was actually application of learnings from what we'd picked up in the previous two to try and develop a tool. So we ran that in parallel, which was part of the SECLI-FIRM premise, that we have a live tool and an existing system. We ran those in parallel for a rig move in September. And then not mentioned here, but we also have followed up in August last year with electrification, so cable running operations from a shallow water site on the beach, running a cable out to a platform to electrify that, to remove diesel generators. As I've said, most of the issues that we have to deal with internally, because we're not dealing with the science, is the communication of how these things are developed by the end or for the end users, and the distribution of the results, because these you're talking to people who need to make a decision there and then about whether or not they're going to extend a campaign of a rig, for instance, for $100,000 a day. Whether they extend that or they just say we cut our losses and leave. So they need something quite crisp. But we need the science to understand what to tell them to make that decision. If we're looking at costs, we obviously have a direct appreciation as end users of the cost associated with a good or a bad forecast. We can look at something like the graph at the top, and as I said, we can work on the basis that it's better in the summer than it is in the winter, but also linked to that there is a supply and demand, which I'll come back to in the conclusions. And the other interest that we had obviously was to look at improving on traditional approaches. We use deterministic forecasts, we use ensemble forecasts. They have some limitations. Sometimes we use teleconnections if we're really getting desperate. We say, what's it going to be like in the next few weeks? Are we in a positive or a negative NAO, and what impact is that going to have on our operations? And while we were developing these tools, we were obviously concentrating on how to convey those learnings both internally and with other end users in the industry. And as I move into wind, that becomes more relevant because there are more end users and their operations are so much longer, so seasonal forecasting becomes even more important. Now, if we briefly look at some of the results that came out, first we had several workshops. In one of the first workshops, we developed decision trees for all of the case studies, and this just gave us a clear flow chart for, well, in our case, we have climatological data, we've got models, and we use that as wind and wave inputs to conditions, to decision-making processes based on different thresholds for different activities. So deciding whether or not we postpone, or whether or not, if we don't postpone, what's the probability of success. So that was a useful tool to provide us with a decision-making process, but also give us commonality across the case studies. We have, with the Met Office, previously looked at cost loss analysis, and Jess, I think, will speak a bit more about that. But the other thing that this tool provided us with was whether or not we balance schedule versus cost. If we have to get something done, do we just say, right, we're going to spend as much as we need to get it done? Or do we prioritize a different project because we can't work in a certain area? And as I've said, links with KNMI and TenneT were very useful because it reinforced in a similar environment with a different industry, it reinforced the benefit of having the partner involvement in these case studies. Jess will also come back to this in a bit more detail, but looking at some of the, in a very high level, some of the results that we were using, we have these, the graph at the top is exceedance based on climatology. So the curves are going out 40 days, I think, from ERA 5. And if the line associated with the climatology is above, then the forecast is higher. If it's below, the forecast is lower than climatology. So you don't necessarily need to say, what's the significant wave height in 10 days time? Is it going to be 2.4, 2.8? You need to know whether it's higher or lower than climatology. And we can use that and the graphs underneath to give us a better understanding of how to use the data. One of the initial results was that it looked like shoulder month forecasts were more effective in the spring, so moving from winter into the spring rather than from autumn into the winter. And we also looked at, obviously, skill versus useful skill and what we can communicate in terms of benefit for end users. I've mentioned economics and the huge variability, but we did some, as I said, Nicholas did some work for us. We obtained daily AHTS's anchor handling vessel rates for the North Sea. And the graph on the right shows different years, 2019 back to 2015. And you can see 2019 was a very flat year. The scale on the axis is the same in terms of day rate, the y-axis. So you can see the variability between years, you can see the variability within years, and also the fact that there was not necessarily a seasonal climate link with that. We think, we're fairly certain that that's partly due to weather, it's partly driven by availability, but also macroeconomics that drive whether or not maintenance is required offshore. And that's historical, but it will probably be different with offshore wind. But there are also things like vessel owner priorities. Do they think they can earn more money somewhere else, and they move their vessels somewhere else? But basically, all I wanted to show was that there's a huge variability, and weather wasn't necessarily a huge part of that. So in conclusion, we found that skill at a seasonal level for our application still needs to be demonstrated. There are some improvements, and we are trying to use those and implement those as tools. As I said, skill may be better for the coming out of the winter than coming out of the summer. But key in developing confidence in our end users is we need to test on future projects, and we need to find repeatability. But most importantly, we need simplicity and interpretation, which is where we take the science and we try and use that. As Daniel said, that's not necessarily easy. So those were the points I wanted to cover. Happy to take one question or.
So this session now, we're going to have a couple of talks. Another one from the utility sector, and then one from the Met Office that hopefully will tie things up, bringing the users and the forecast together somewhat before we have a sort of discussion towards the end. I should say that the final discussion, the people in the first 3 rows won't be able to see people sitting on the stage, so you may need to shift back when it comes to that point. Right, so. To start with, then, we have Ian Savage, So Ian has been in the utility sector for quite a few years. I won't mention how many. I think you put it on your bio. Originally in the nuclear industry, but now quite spent a lot of time in the water sector, where he works on sort of forecasting production and outage issues, I guess. Yeah. Is that fair to say? So look forward to your talk.
Thank you. Good afternoon, everyone. Thanks to the Royal Met Society for the invitation, and thanks to ECWMF for hosting. We're going to talk about, again, the use of subseasonal forecasts to improve operational decision makings, but this time in the water industry. I think having sat through the other presentations, I'd be interested to see the synergies and differences and the challenges that we face. So why do we need subseasonal forecasting? It's because of incidents like this. So John's already talked about the beast from the east, and it had a massive impact on the water industry. And the regulator was rightly none too pleased. The customers were impacted and were out without water for sometimes 2 to 3 days. If we'd known further in advance, could we have been better prepared? Probably yes. And could customer impact have been reduced? Probably yes. So how weather drives variability in demand? So demand it's got 3 components: base demand, which is everyday usage that we use for washing, toilets, clothes washing, dishwashers, everything that we would do every day, not dependent on weather. The weather dependent usage, which is, affected by the sun, temperature, dryness, and something called freeze thaw, we'll talk about a bit later. And another component, which is weather dependent leakage. So it's not actual demand, but it's how the weather impacts on the leakage, which obviously in winter we get bursts due to the drop in temperature. In summer we get bursts due to ground movement due to dryness, and we get seasonal leakage. That's another component, which is it's a slightly different issue in that all the water mains in the system are joined together with joints. And when temperatures drop during the autumn, the pipes contract and these joints open and weep. So we get a phenomenon over the autumn period where the background leakage increases. Then in springtime and temperatures increase, the pipes expand again, the joints seal themselves. So we get a drop in leakage as well then. Demand risk envelope. This is a bit like Daniel's explanation of how demand can change, but this is all weather dependent. So the two grey lines are the extremities. So, this is based on 15 years historical demand data. So what we can see in summer, the red arrow shows us where demand could be. And there's a massive difference between 2,300 peak and 1,800 minimum demand, and that can be on any one day, depending on the weather. Interestingly, in the winter, the blue arrow, the span's even greater. So, in effect, when we had the winter of 2010 to 2011, over that Christmas period, we would have now, if we had the same weather, demands in excess of 2,400, and you can see similarly the drop down at Christmas there. So we could have demands lower than 1,800 at the same time. So, there's a massive difference in the possible demand levels. So the solution to our problem, and again, you'll recognise this from John's presentation, is this risk assessment against climatic average of higher than lower demands, and this was developed by the Met Office by predicting the occurrence of large high and low pressure systems that affect the UK. A product called Decider, which gives us a 6-week look ahead as to the risk of demand being higher or lower. So when the relationship exists between particular weather patterns and a business impact, i.e. in our case, demand for water, a tool can be developed to communicate the risk of that impact occurring against climatic average, allowing more informed decisions to be made. So we've got a sample of the value of the service. So last year in February, we got the first indication of a risk of increased demand due to cold weather on the 21st of January, 14 days prior to the event. So that gave us 2 weeks to prepare. So this was the first positive. We started getting the service in November. So this was the first positive result. So it allowed us to increase production levels, curtail maintenance, and raise storage levels so that we could cope with the increase in demand. So this was a difference, if you like, because this had the potential in February 2021 to be everything as bad as the 2018 beast from the east. All the indications were the same. The fact it turned out not quite as bad, but it was still quite severe. But in this case, we had no customer impact. And it also allowed us to do some other things, as well as the conventional things about what we would do in-house. It allowed us to put comms out. If you remember February 2021, the worry we had was we had lots of office blocks, we had schools, we had factories with no one there because of COVID restrictions. The issue would be is if we had frozen pipes which then thawed and leaked, we would have empty buildings that where water could have been running for days before anybody noticed. So we put these comms out through social media, asking people who had unoccupied buildings to make sure that they were checked and that any running water could be switched off and turned off and isolated. Another positive example, we came in May last year. So on the 17th of May last year, you can see this is quite a massive signal. So from the 26th of May all the way through to the 22nd of June, we were either red or amber. Once again, luckily in advance, we had a nice green phase of low demands, which gives us time to build up our production levels, build up storage and react. And again, demands rose to quite a high level during that period. And again, we had no customer impact. Next steps on the journey. Because of these positive results, we were able to apply to the Ofwat Innovation Fund for funding to expand the use of the service. So we've won the bid and we're now going to expand the service to 9 other water companies over the next 2 years. Starting really soon at the end of this month. So we've got United Utilities, Severn Trent, Southern Water, Northwest, Southern, Bristol, Anglian, all coming on board. Also, from the funding, we're going to look at the potential to use the technology to other uses, potentially flooding events. So if we can use it to predict demand, can we also use the same technology to predict surface water flooding? Once again, we can prepare, we can make sure that we've got assets available, we can make sure that we've done our groundwork ahead, we've cleared gullies, we've looked at hotspot areas, we've got maintenance, we've got resourced up so that, well, again, this is in the early stages and this is currently sitting with the Met Office. So that sort of completes my presentation. I know it's probably a bit quick, but it gives us more time if anyone wants to ask any questions. Thank you. Shanti?
Thanks for sharing that, Ian. Just a comment or an observation. So is the other water companies not using something similar that you're using?
No, the Decider product from the Met Office is the only one that's using this technology. They may be using subseasonal forecasts in the conventional way, but not on the pressure systems that we are now. The Met Office have actually identified that only sort of 3 or 4 of the of the 50+ weather patterns available link to increasing demand. So if we can which they can, predict the probability of these weather patterns occurring, then we can, it's transferable to all the other water companies as well.
Okay, thank you.
Thank you.
Thank you. Any more questions from the audience? I'll bring the mic up.
I think the thing with water companies, which has been in the news a lot, has been a releasing of untreated water because they don't have enough capacity to process it. Do you think that there's any possible use for seasonal forecasting?
Yes,
to address that?
Certainly the same technology. If we're looking at surface water flooding, that would be at the same time where the sewers have become overloaded. So similarly, we may not be able to stop it, but we may be able to mitigate and reduce ahead. That's a really good point. Thank you.
I've got a quick question, Ian. So you were sort of saying that maybe, other water companies might start using similar information. Would that put some kind of competition on resources if they're all using the same forecasts, or?
There's quite a few legal loopholes to go through at the start of the project. We've got to sign collaboration agreements with the Met Office for use of the decider product, and a collaboration agreement between all the water companies, between each other and the Met Office. So, that's all been covered off as part of the agreement.
Okay, that's interesting. Okay, so we're now going to move on to Jess Amis, who's working at the Met Office, particularly in the marine services sector, looking at, well, I think seasonal and also an interest in the climate aspect as well, but I'm not sure you're going to talk about that. So, yeah. Yeah, before that, Jess was in Australia doing a PhD on sea level rise or something like that. Sorry. So, yeah, okay, thanks very much.
Does that sound okay, about a good distance? Cool. Yeah, so thank you for the introduction and thank you for having me here today. Before I start, I'd just like to point out that a lot of the work that I'm sharing has really been work that's come from a lot of different people. So I'd especially like to mention Hannah Brown and Ed Steele from the Met Office, who were really leading a lot of the work which I'm going to talk about from our side. And also John, who we heard from earlier. As our main industry partner, his insight has been really valuable with everything that we're going to discuss now. So yeah, SECLI-FIRM's already been mentioned a lot of times today, so I won't go too much into the background of that. But just to point out, so the Met Office did work on a lot of these case studies. The one that I'm going to focus on in my talk was one I was involved in and which John spoke about earlier, case study 7, which was looking at wind and wave conditions. And yeah, John mentioned as well that there was some overlap with case study 6, which was worked on by KNMI and Tennant. Yeah, and that was really great to have those discussions going on with them because a lot of what we were doing did have a lot of similarities. So yeah, one of the big highlights that we found with this project was really working in close collaboration with Shell. So I saw this diagram from a colleague, and I think it suffers a bit from what Antonio mentioned, the co. But I think it's actually really nice to sort of describe this co-production process, which was really valuable during this project, and yeah, just helps us visualize in a way the process that we go through, and that it's not actually this linear co-production process, but it's actually a really iterative process. We go around several cycles of this rather than just working through it as like exploring the need, getting a solution and then evaluating it. So throughout the talk, I'll sort of be referring back to this and hopefully give a bit of a flavour as to why that ongoing communication was so valuable during this work. So again, sorry, there's probably going to be lots of bits that pop up that other people have already shown in their slides. So John has already shown the decision tree, which he introduced us to at the start of the SECLI-FIRM project. I just wanted to refer back to this, as at the beginning of the project, this was a really great point for us to start from. It helped us understand the decision-making process which Shell goes through, and it helped us understand the processes with which any forecasts that we develop need to fit into, so that they can be integrated and of benefit to the user. Okay, so starting at, going into the science side a bit more. So yeah, again, weather patterns have been mentioned. So as forecasts are improving, we still have this limit to, when we're looking at longer timescales, getting that predictability for small scale weather features. What we do have more, there's just an inherent predictability at longer timescales with larger scale atmospheric circulation patterns. So yeah, this is the Met Office set of 30 weather patterns. And the value of these when we're looking at extending forecasts is really that they can be paired up with an ensemble forecast system. So Ian mentioned the decider tool. This is a screen grab which I got from it on Monday, where it's using the weather patterns alongside the ECMWF forecast. So what it's doing here really is each ensemble member is matched to the closest matching weather pattern. And this allows the forecast to be simplified into a series of probabilities for which weather patterns or regimes are most likely to happen. So on Monday and Tuesday, we can see we've got this 200% for regime 22. So this is a cyclonic southerly with a low the west of Ireland. So we know that the forecast is saying there's 100% likelihood of that happening. As we move further into the forecast, we see there are some weather patterns which are more likely to happen, which are shown by the darker colours. However, some of the ensemble members are starting to show different alternate scenarios. And as we go further into the forecast, there's a greater deviation in the ensembles. So we've got more potential scenarios. So what we did for case study 7 was that we took these weather patterns and we looked at matching them to basically the wave climate which is experienced under each one. So we did this by matching historic daily weather pattern data with a wave hindcast. And so we took the maximum significant wave height for the historic period under each weather pattern. So figure A, you can see the distributions of the different maximum significant wave heights experienced under each weather pattern. So the line, which is maybe a bit faint, but that's showing a significant wave height threshold of 2.5 meters, which can be changed dependent on the user's requirements. But we can already see that under some of these weather patterns, there's a greater likelihood of the waves exceeding this threshold than others. And figure B also is showing this same data, but a different type of visualization, this time probability distribution functions, showing the probability of significant wave heights being exceeded, the different significant wave height thresholds being exceeded for the different weather patterns. And then what we can do with this information is, so we can get a single daily value for the probability of a significant wave height threshold being exceeded. So by taking the probability of the significant wave height threshold being exceeded under a single weather pattern, we can then multiply this by the probability of that weather pattern occurring, and then summing this across all of the different, each weather pattern, then that will give us our our daily probability of exceeding the threshold. So one big assumption with this method was that it assumes that waves are related to the conditions on the day. So this is it's sort of justified for the North Sea, which was where we were focusing. This area is really dominated by the wind sea environment as opposed to swell. But we did want to investigate this and make sure that this approach was valid. So we did this using a wave age index. So the wave age index is calculated from the wave field. It basically gives us a value. If it's below 10, it's suggesting that the wave field is related to the weather on the day. Whereas if it's above 10, so if the waves are related to the weather on the day, they're young waves. So whereas if they're related to weather on previous days, so if it's a more swell-dominated environment, we're getting older waves. So we calculated this again for the historical period and stratified the results by weather pattern. So using this, we can see that there is a wide spread of different wave ages under each weather pattern. However, all of these are very much skewed towards the bottom, towards younger wave ages, with the median values for each lying under this sort of wave age index of 10, which is a rough limit between a young wave system and an older wave system. So this sort of does validate the method we use. What it also does is it highlights that some weather patterns, so for example, like this cluster here, are much more related to younger waves. So this means that these weather patterns would be much more reliable for this type of forecast. Some of these ones which start to extend into the older waves might need to be a bit more wary of. So I just quickly wanted to show some verification. As Anka said, there's lots of different verification methods that we can use. What I've done here is focus on the Brier skill score, which is looking at the skill of the forecast. I think this is one of the easiest as an initial look just to interpret. So just going to show this one today. So here we're comparing the weather pattern based significant wave height forecast, which we came up with for this case study, with the direct ECMWF forecast. So as expected, for shorter lead times, we're seeing that the direct forecast is a lot more skillful. This is, of course, with the weather pattern sort of downscaling method, we're losing a lot of that fine sort of detail. However, this is generally an area where we have good forecasts in place. People have ways of looking at this time period. When we get out to longer lead times, past about 10 days, the weather pattern and the direct forecasts converge. And looking, sorry, I should have mentioned this is for a significant wave height threshold of 2.5 meters for a single site. When we look across different sites and different thresholds, the weather pattern forecast tends to actually be slightly more reliable. But the main point is really that they converge here, which is quite interesting, seeing as the weather pattern forecast is so much more computationally lightweight. And another interesting thing that came out of the verification here, which John did touch on in his talk, was the difference between seasons. So yeah, as John mentioned, we were really interested in looking at the shoulder season specifically for this case study. So here I've included the Brier skills scores for spring and autumn. And we can see that there's quite a big difference in these. And this was something we were seeing across all of our different verifications, that spring was more predictable than autumn at longer lead times. And this is kind of a good thing, because if we can help Shell or sort of move their operations further forward, this is somewhat easier, because then the operations can extend into summer, which is the normal sort of working season. Whereas if we instead extend it into autumn. If anything goes wrong, then, you know, winter starts and conditions get worse, so there's less sort of contingency there. Another thing that we looked into was what was the value to the user? And again, this has been mentioned in some of the previous talks, that skill is not always the same as value. So what we did here was that we looked at the relative economic value of the forecasts. And again, this is for both the direct ECMWF forecast and the weather pattern inferred forecast. And this is based on user-specific cost loss. So just to quickly introduce that sort of term, if we've got, so say for offshore operations, if we have a planned operation and because of a forecast coming out, the operation is postponed, that would incur a loss. No, sorry, that would incur a cost. Whereas if the operation goes ahead, but a weather event happens and exceeds the threshold that we needed, that would cause a loss. So it's really this ratio between those two, which this is reflecting. So if we've got a cost loss ratio around 1, basically the user would be much more likely to go ahead with operations, even if there was quite a high risk of an event occurring. Whereas if we're at the lower end of this scale, either the cost of postponing a procedure is quite cheap, or the loss is going to be very big if the event does occur. So, so the user will be more likely to postpone the offshore operation. So for the offshore industry, we're generally looking at around 0.1 for a cost loss ratio. This really does change with what the operation is, who the user is, of course, and many other factors, but that's sort of where we're looking in general. So this relative economic value here is showing if we've got 1, it means that we've got a perfect forecast and every decision we made is perfectly informed. If we've got 0, that's the same as acting off of climatology. And this is showing the value at a lead time of 28 days, which is quite interesting because even though we had, like when we're looking at our verification, our skill is saying there's basically no skill in the forecast out at that lead time. However, the value to the user is still, there is still some value to the user there. However, the caveats here is it is very much dependent on the cost loss ratio of the user and also the significant wave height threshold in this case. So you can see these different colours represent different significant wave height thresholds. So it really does, it's very specific in a way. Okay, so moving on to the visualization of the wave forecast. This was something which we had a lot of different goes at. So we came up with our initial visualization of it. And for several months, we passed these on to John so that he could sort of test them out at Shell, see if they could be incorporated, how other people felt about using these as well. And over time, we sort of, it was really beneficial for us basically to have this feedback, having it used or tested out by the user. So we could use that feedback and sort of iteratively improve how we're visualizing the forecast and what information it's showing. And going back to our little co-production process, this is like really an example of how it's not linear. We're really like building on the product each time, sort of reevaluating, redeveloping, and then trying out a new visualization for it. And in the end, at least at the end of the SECLI-FIRM project, this was the sort of forecast tool that we'd come up with. So we've got at the top our significant wave height forecast. And as John briefly explained, this shows the probability of exceedance of our significant wave height threshold, which here is 2.5 meters, and this is shown in comparison to climatology. And one of the sort of things that we incorporated in the end was this shaded, so we've got the previous forecast shown in different shading, so you can see, the user can see the consistency which is coming through with the forecasts. And something else which got added, which also was useful, was these circulation trend information which came out of the weather patterns as well. So we've got information there on the pressure trend, the zonal and meridional trends as well. And this is really complementary. So this was actually the forecast that was used for the case study that we looked at with Beast from the East. So we could see, obviously here, we were looking for clear weather windows in the waves, but the wind or the pressure trend information was providing a lot of information about what was going on there. So we could see that that easterly coming through very strongly. Yeah, John also mentioned some of the other trials which was done for like the Shell rig move, and something that was actually quite interesting about that one, I think it was the 2020 case, but anyway, that one, as well as providing this sort of forecast, the operational meteorologists at the Met Office also provided a sort of summary about that to include a bit more background on what was going on with the weather systems here, and yeah, why sometimes the forecast might be less reliable, what the main drivers were, and I think that was quite well received as well. So now I'm just quickly going to go through some work which sort of was, the ideas were there at the end of the SECLI-FIRM project, and it's been built on since then, especially by Ed Steele in our team. And this is this idea of a dynamic forecast trust index. So this came about because sort of through the evaluation process of the SECLI-FIRM work, how while we can, it's easy to sort of use these forecasts in retrospect. So for the Beast from the case study, for example, we can look back and be like, oh, if we'd had this at the time, we would have seen this coming through. But when it's actually, when you're faced with that in the future, how do we know how much trust to place in that forecast? So that was what we're trying to sort of address with this work here. So we've got this sort of Venn diagram of information which we have at the moment. We've got the previous performance of the forecast, so that sort of, which was displayed in a way the verification that we showed earlier, the Brier Skills Score. However, this is just evaluating what has happened in the past. It's not telling us whether the forecast in the future is going to be correct or not. And then on the other side, we've got ensemble models, which are now giving us that ability to have that sort of the quantification of the likelihood of different weather patterns or weather scenarios happening. But again, when we've got all of these ensemble members and a sort of range of possibilities, how do we know what's the actual signal and what's noise? And what we sort of end up wishing for is something which incorporates both of these, almost like a forecast of a forecast, if that was possible, to tell us how good our forecast actually is. And that's sort of what we're trying to do with the trust index. And again, this is sort of showing how, even though we've reached the end of the SECLI-FIRM work, we're sort of still building on that. So we've sort of started co-exploring this need again, and we're now developing a new solution for the gap that came out of that. So the way that the trust index, the way that it works is basically looking at the difference in predictability between different, or how reliable how reliable the forecast is under different weather patterns. So we already mentioned that a bit before, that some weather patterns have better wave predictability than others. So we can look at that either looking at the skill under the different weather patterns or under the skill of, for example, here we've used the main pressure trends, but it could also be changed to a lot of different things. We could use here each of the 30 weather patterns. We could look at a smaller set, or even do something like looking at the North Atlantic Oscillation and using that instead. So it's sort of looking at how the skill varies under these different weather patterns, essentially in different ways. So here, just to illustrate this, we've got the skill score, and if it's at 0, we've got a forecast that's the same as climatology, or essentially as valuable as climatology. And the skill improves as we go up with like darker shade of red. And just a couple of examples of how this is looking to be used. So there's a lot of information and detail on these, which I'll just briefly describe the main features and how the dynamic forecast trust index fits into these and adds additional value. So on the left-hand side, we've got a wave height forecast from our different ensemble members. These are shown in grey. We've got blue lines to show the 5% and 95% probability envelope. And our red line shows the threshold, significant wave height threshold that we don't want to exceed. So we can see that, basically what's been added here is this trust index bar at the bottom, and that's showing us that the first part of the forecast has very good skill, and then this decreases, and around 7 days, the skill is then equivalent to climatology. And so on the right, this is the same forecast time, which hasn't been, this was picked just because it was the first week in January. This hasn't been chosen for a particularly skillful example of this. But yeah, the same forecast on the right-hand side, which is showing us the probability of exceedance in blue. And then the user-defined acceptable risk at 95%. And then here, as well as the trust index at the bottom, this has been translated into a go or no-go scenario here for the user. So when so basically, again, here we've got that the user should go ahead with operations for the first 4 days, and then after this, the risk of the waves exceeding the acceptable threshold is too high. So I think that's it from me. Yeah, thanks again for having me, and happy to answer any questions now or hand over to the panel.
Thank you, Jess, for a clear presentation of the method and the results. I was just wondering, looking at your comparison between the direct forecast of wave height and that using weather regimes, did you try to do it using the same model data? So you could have probably calculated the weather regimes, the weather patterns from the same model from which you took the the direct forecast, and seen if it is the weather regime clustering that is potentially reducing the scale, or is the model itself?
Yeah, so the weather, sorry, I should have said this actually, but yeah, the weather pattern clustering that we used was from the ECMWF model as well. Yeah. So yeah, what we should have been seeing in that difference in scale should be directly down to the weather pattern. Yeah. Thank you.
Thanks. Nice example. Did you calculate the continuous varying probability skill score on the actual forecast data over the last several years, or over hindcast data?
I believe it was the forecast data, but just for the last 4 years. Okay. Yeah. That's good. Yeah, I'm not 100% sure, so I can get back to you.
I've just got a question. I think it applies to you, Jess, and John. I don't know whether you want to take it up at the panel discussion. Your trust index that you had there on the last but one slide. I don't know, has Shell gone to the next stage of putting financial penalties and cost to this? Or is that too early at this stage? Or is there something the industry is talking about it, or the scientists are looking at that? Because then the big question would be, you want financial penalties or gains, isn't it, with those risks? So is that too early, or whether it's something that's been thought through?
Sorry, I should just say this is very early stages work. So this hasn't, I don't think it's passed it on to you yet. No, sorry, we're still sort of, this is the first trial of this work.
Okay.
So yeah, as I mentioned, it's just been done for this example at the start of the year. It was really sort of more of a proof of concept type thing at this stage.
Because I mean, that's the
I
key
should have
in the
made
long
that
term,
clearer.
isn't it? Because in the long term, that's the key, isn't it, for John to make a financial decision saying yes, no, or
Yeah,
chance of going ahead or not.
yeah, definitely. And I think that's what we're trying to capture here with the sort of the acceptable threshold that we've got there is sort of reflective of that a cost loss ratio type thing of like how certain we have to be to make a move. That's not the right word for it, but yeah.
No, it's a good way of looking. As a trust index, right? That's a concept I've not come across, but yeah, it's good for sharing that. Thank you.
Any more questions? Yeah, well, it was very, very interesting to see that, you know, the idea that you're getting a sort of cost loss ratio. I'd be interested to know how robust it is among, you know, over different events and different thresholds and lead times and stuff like that. But it's certainly a way that we can sort of connect with users if that's it's a possible way of going.
Yeah, definitely. And we did explore quite a lot of different thresholds and different ways of visualizing that as well. It's actually, if you want to read the SECLI-FIRM report, but
is that the free one? Is that?
Yeah, there's more detail there, but also happy to pass that on to you as well.
Okay, thank you, Jess. All right. Okay. Well, let's just thank those the speakers one more time for. Okay, so we're going to have a bit of a question and answer session coming up. So the idea is that the speakers will be on the stage and we'll have some questions. So please think up some questions to get the thing going. In the meantime, I realise we haven't got quite enough chairs on the stage, so I'm going to try and get a few more chairs. And Alberto is going to lead the discussion. So maybe if I hand it over to you.
What I want to do is to go back to some of the main questions we raised with the meeting, not so much the details of how much is the scale here and there. So some of the key questions that we discussed are the role of science, how much is science contributing to the decision making, how much instead is the role of the interaction with users helping bring out some of the science that may not be perfect, but enough to take that and use it for decision making. And the value also of the forecast we discussed, but I want to broaden in SECLI-FIRM and other projects, we often look at the economic value because it's in a sense an easy target, we can measure it. I want to broaden that to more social value. So one example is we used the forecast, we tested it, the economic value was not so clear, but we still think that having a forecast system is valuable for our operations. So that's goes beyond the economic value. You take a decision, you take the decision to actually invest in that system because you think in the long run is going to help you. And that has a value in itself, which is not economic, at least as you measure it now. So I want to open the discussion, just first thoughts on role of science, interaction, particularly in SECLI-FIRM project. How much do you think the science, the value science has played in involving you in the project, you know, your involvement and the fact that you were interested in using this versus the fact that you think that, you know, having understood better how the forecast works, you know, and be involved. You found it easier, go beyond the science and the limitations, and so that helped you use the output better. So first round, very quick, John, everybody, and then we'll start taking questions from the audience. Please, John.
Well, I deliberately left the inclusion or the amount of science, the content, quite light in mine, partly because Jess is the expert, I'm not, but also because it allows us to show the difference in the approach. So, for instance, the weather patterns is not something that we thought about. We didn't consider the fact that rather than forecasting a wave height 10 days ahead, 14 days ahead, rather than forecasting the conditions that then drive that wave height are more important. And things like the wave age, that's also very important. So those were two key aspects that came out from the science that were not driven by industry.
Good, thank you. Dan?
I'll take a slightly different approach. So the crucial part for our project was the interaction from the very start. So talking to the Met Office, they could tell us that they had skill in their product, but we knew that it would be hard to tease out that skill into what we needed. And so we were able to develop the project in a way that they could then demonstrate to us that there would be skill in our forecast, and we could then build the product together that would give us the results that we needed. And crucially, having them involved all the way through, when the forecast didn't turn out to be any better for that particular year than if we hadn't used their product, we were able to draw on their expertise to help explain it internally, why that was the case and why we shouldn't just throw it out based on that 1 year.
Great, yeah, thank you. From your perspective, Jess, I guess from the science more than
Yeah.
how did you see the science being used? And
Yeah, I think sort of as has been like the theme of this day, I think it really was the communication all the way through. While the science is obviously important, I think for us it was important to communicate how the science works to John, so that from their side they understood where the forecast was coming from. But similarly, while we had the science, we wouldn't be able to implement it in the way that was useful and could be integrated to Shell's workflow if we didn't have that knowledge coming in from the industry. So I think it's really like both sides coming together to bring value to this sort of work.
Thank you.
Yeah, just to reinforce John's point, it was, if anybody had said to me that the end product would look like this at the beginning, I wouldn't have believed them. So I naively went into the project thinking all I want is a longer forecast, quantitative, telling me what the temperature is going to be, because I know the relationship between water demand, temperature, sun hours and rainfall. So why can't you just tell me that? So, I think going in like that sort of meant I had a lot to learn, but learnt a lot. Similarly, we talked about the successes during the approach, but what I didn't mention was the times when it wasn't successful. Now, thankfully, we haven't had any times where we've had rapid increase in demand that wasn't forecast, but we have had forecast high demand that hasn't appeared. Probably 3 or 4 times. So probably equal amounts of successes and non-successes, and there's a cost associated with that. So preparing for something that doesn't happen comes with a cost, but we're willing to accept that cost because it secures customer supply. So I think, hopefully that answers your question, Alberto.
Yeah, thank you. Yeah. Okay, Anka, we didn't mention Anka was actually marginally involved in the project also in terms of in your role of advisory board.
So I haven't heard any of this for the first time today, but I will, even based on just what we heard today, I'm prepared to draw 2 conclusions. One is that, so coming at it from the service perspective, we didn't do the basic science, nor did we do the application and the decision, the modification of the decisions in light of this information. However, it struck me from the beginning, and today I wasn't the only one, decisions in user space do not care. It's a seasonal forecast, is a monthly forecast, is a medium range forecast. So filling the gaps in the timescales we present and giving people information that is aligned to the timelines they have to work to, rather than structuring it by our compartments, is important. The second thing is something that Ian said, and sorry to take 2 points here, but I think this is a really good example about how the verification for the user interaction needs to be different. Not that in the science, in a sort of absolute term, you would do a verification that only looks at successes or that only looks at correlations and the like, but it's important to look at all the facets, to look at false alarms, to look at misses, not just to look at case studies. Oh, I have an event, did I forecast it? You want to see that when the event didn't happen, you didn't forecast the same thing, exactly what you said. So I think in order to get users' trust and reassurance, you need to analyze these things in all the ways, and you learn about how good your system is or not in that way.
Okay, thank you, Anke. And just as Anke pointed out, we actually, for the eagle eye, you notice that when we talk about seasonal forecast, we use it in a kind of loose sense. In some cases, it was a pretty short range, but the point here is that what we try to do is to, again, take the applications from the point they were and try to move farther. So there was no point in saying, oh, you're doing now 1 week, let's do 3 months because we want to test that. You know, it's much more effective if you take it step by step and we walk all the way through. And eventually in a few years, we'll get to 3-4 months and so on as the science improves as well. So we can take some questions from the audience if there are.
I think from me, I was part and parcel of this project as well. For me, at the beginning, we had a lot of discussion in terms of how science is going to get closer to the users. And I think what you achieved in this, what we achieved in this project is science and the users community are much closer now than they were, say, 5 years ago, 3 years ago when we started the project. So that's a positive sign. And we're not there yet. There's still a gap. And we need to bridge that gap perhaps in the future as well. So that's something we need to take it forward. In terms of the decision-making process, John, Daniel, and Ian talked about, you sold part of the output to the users. They themselves, I'm sure, have to go and sell that output or the decision-making process to the next level within the company, whether it's Shell, National Grid, or Thames Water. And of those 3 companies, I mean, National Grid and Thames Water are regulated business, right? So when a company goes to a regulator saying, right, we can make better decisions, and the first question they normally ask is, what proof have you got? I mean, how can we be so confident that you can save £2 million or 10 million pounds to making the decision? By having that science will give them confidence in terms of long-term investment. And I'm sure it will happen to apply to Shell as well, that at least they have got some evidence to go to the regulator and saying we can spend more money and get better results, which in turn gives reduction in consumer spending, or reduction in the company spend, and which in turn helps every customer, UK PLC. So I think the final benefit is still a long way to go, but that's where I actually see the journey. I don't know whether it makes sense to the panels or not. Okay, I'll leave it at that because I'll let other people speak.
Thank you. Thank you, Shanti. Ayla, sorry, Elizabeth first. Sorry, I didn't see Elizabeth's hand. Yes.
No worries. I was just curious in regards to what do you see as the next steps and what would you like to see going out of today and in the future? I don't know if that's a question that we were.
Yeah, very good. If I can, maybe, is it directed to someone in particular? Everybody?
Yeah, thank you. Yeah, I mentioned the next steps about taking the service out to other water companies, but also we need to, as Anke said, we need to sort of fine tune the service. So we got this raw service at the end of SECLI-FIRM and it hasn't been looked at since. So it needs to be evaluated. One of the things that I probably didn't mention was that the risk of, maybe I did say that the risk of a high pressure weather pattern is not weighted. So a high pressure pattern in March doesn't have the same impact as a high pressure in July or June. So there's work that we can do to weight it for the time of year. As you saw, our demand envelope, it's up and down like a ski slope. So we can weight the effect of the weather for the time of year. So there are definite improvements that we can make to the service as well. Thank you.
Thanks. Maybe do you want to, in your field, reply? I mean, where are you taking the seasonal forecast in 10 years, for example, Anka? What's next? How much skill can you give us in the next 10 years?
This much. Yes, no, people are trying to, I mean, let's just step back a bit. We have here sampled the benefits of using seasonal forecasts in Europe, in a very small part of Europe. There are parts of the world where seasonal forecasts do offer more value. And you probably need to go in the tropics, to go to Australia to find how users actually use seasonal forecasts. And there you'll find that there's a lot of information people can get out of it. Seasonal forecasts are done as global simulations. So they do have this value. How long before in Europe we can do much better than we do now? Quite a while, I would say. But we are doing everything we can. And as you know, you can't just start, oh, I want this much skill, and I can work back the recipe as to how to get it. So all the sensible changes are made to models, all the improvements to initialization, to the model representation, including increasing resolution wherever possible. But there is always a balance to be struck between the costs and the benefits. And if there are parts of the world and times of year and types of climate where you can't predict things, probably that's not going to get perfect anytime soon.
Okay, thank you. I should add that actually we also had Colombia, South America in SECLI-FIRM. So we had a sample of tropical conditions, and it did show better results indeed. And you invited also people to Australia. I do as well. It's yeah, please go, and it's a great place. Science. What do you see your science? I know actually you had there was an additional work that was not shown today that showed some promising skill beyond the weather regimes, no? And in for case study 7, we're using a statistical approach, no? Okay, so maybe you're not across that. Okay,
Sorry.
yeah, someone else. Okay, so from your perspective, how do you see the science used in?
Yeah, so I guess coming from the part of the Met Office I work in with the industry consultancy, I think actually this builds a bit on what Shanti was saying about SECLI-FIRM being like a great first step at bringing industry and science closer together. I think for me, the next step would be, yeah, continuing to bridge that gap. I think that's what we're trying to do a bit with this anticipated trust index, sort of helping to build user confidence, I guess, and this relates a bit to what Ian was saying as well, how to, yeah, I guess building the user confidence in the forecast products, which again comes from both sides, I think.
Okay, so improve and use the trust index, yeah? So that's your target. Good. We need to make it mainstream.
Just building on that, and exactly what Shanti said, I have to sell this product internally at National Grid. We've been running it offline. It's not operational. The next step is to convince people that this is a product that we need to be using, get managers to sign off, and then it become operational. That's a big job, building up the trust on something you don't have a huge amount of. How do you assess the performance? We need to do some backcasting or some analysis to convince them. We've only been running this for 2 years, and both years weren't brilliant results. So it's a big sell, and that's Met Office are helping a lot with that.
Thank you, Dan. John?
Thinking about non-oil and gas, but thinking about sort of wind and generation, energy supply, and balancing the grid. I suppose from a wind point of view, it's pretty important to look at seasonal, and how we build into projects, whether it's trading or storage, combination of generation and storage, seasonal will become pretty important there. And I know there's some ideas in the audience as well.
Very good. Thank you, John. So let's move to the next question from Ayla, please.
So it's lovely to hear that science is progressing and making a difference to end users. What I'm hearing from the industry is that predictive skill isn't everything that they would like. I mean, we always want it to be perfect, but it's never going to be perfect. And as an observation to the scientists, then it seems like you're trying to take the industry questions and fit them into a paradigm that you already have, your set weather regimes that you already know about and that are defined from a weather point of view. And my question is, what happens if we turn it the other way around, which we've done some work on and University of Reading has done some work on, and actually say, let's let the users define the regimes. So the water companies could give you a list of high demand days and low demand days. John could give you a list of times when he can't move his oil rigs or, you know, whatever's important, significant wave height days. And then what happens if we look at the skill of forecasting those regimes that are important to the users? On the other hand, I'd like to, so to the scientists, why are you trying to fit their question into what you already have rather than modify what you have? And to the end users, what skill scores do you want to see? Like, what would matter in your terms? Do you want a percentage of correct hits, or the percentage of false hits has to be below a certain threshold? What is it you'd like to see as a measure of skill?
Okay, so understood the question. John, off you go.
I suppose one of the key things in terms of building confidence would be repeatability. So, or understanding and being able to communicate why things are wrong, which has come up already. But if we consistently get it wrong, then that tells us something about how we use the forecast. So yeah, a negative result is not necessarily a bad thing, as long as we are confident in how consistent that can be.
Thank you. Dan, do you want to also?
I guess the two things. So the idea of flipping it round, so looking at the events that really matter to us. Yeah, we like that work at Reading. We've been talking about, yeah, peak demand. That's what we care about. We don't care about the lowest temperature in the winter or the lowest wind. It's the final thing for us, which is that peak demand, what's happening to the wind at the same time. So can we focus on the conditions that lead to that and how predictable are they? So I've been looking at that work a little bit. On the metrics of what do we want? Again, this is really difficult because it depends on our application. So we run various processes, and for each of them, we'll have a different metric probably of what we need, because the punishments aren't symmetric. And so we need, I don't like to keep going on about it, but involving the science from the very start, so we can develop a metric all the way through that makes sense for what we're forecasting. And so for the peak demand for the winter, we really struggled to come up with a metric that, because there's so much other variability going on that is dwarfing our weather effect. So could we tease out the weather effect and then just do the metric based on that, is where we landed with the Met Office, and we're still developing that.
Thank you, Dan. Jess, do you want to also?
So yeah, I think that's a really good point about taking, in a way, getting the user's idea of what would be, getting them to define in a way the situations rather than us using what we know, as you said. I think I mean, obviously there's always different ways to approach it. I think one thing would be maybe to define the events. Overall, when we're looking at something like operations, I guess it's not always looking at the exact same wave conditions or wind situations, everything. It's sort of, yeah, not always like exactly the same. And in that case, how do we quantify it in a way if it's not always looking at exactly the same thing? But and I'm sorry, I'm not fully up to date with the work that Uni of Reading is doing on this, so I'd be interested to see more of how that's being addressed. But I think that's probably, yeah, that's why in a way we probably went back to the weather pattern approach for this, using what we know, because we were still looking at a range of different waves, a range of wave and wind conditions. So I think that's why we stuck to that. But yeah, I mean, I think there's definitely space for approaching it from different directions as well.
Thank you, Jesse. Ian?
I think currently the alternative to having subseasonal forecasting is that we have to then go back to climatology. And you saw the massive range of demands we could have at any time during the year, and to be prepared for those would be a massive cost. So you've got to be prepared for the lowest or the highest at any time. So anything better than climatology is worth having on the risk. I think we've been a little bit unfair on the scientists. So the way that we provided the Met Office with our demand data for the last 13 years, and they looked at these extreme events, the times when demand went really high and really low, and hindcast the weather patterns against those extreme events, and that's how we came up with the solution.
Thank you, Ian. And Anka?
Well, I was prepared to guess that there'll be as many answers about what's the skill threshold and metric that people want as there are people answering the question. And this is why the Copernicus Climate Change Service has made a step forward in sharing a lot of data. So we have instantaneous data every 6 hours for 6 months into the future, because I don't think that it's for somebody who sits on the other side to do the skill assessment. I personally believe that it's not ultimately the skill of the weather prediction as the skill in the decision making that matters. So I've been dying to tell Daniel about and to ask him whether he tried to use this hindcast data to try and play the game that he did in real time in the most recent winter over those 20-something years. You only had one example, and there it turns out that you could have made as good or better guess by using climatology. But if you had done that over, you said we need to wait a while to realize the benefit. You can play the game using these 27 years of past data and see if on average over that period, it's still no guarantee that using it in the future, it would be better than not using it. But at least it's some better estimate as to what you might have got so far. So I think collaborating with the users, and even, I mean, for me, the National Grid is a dream case study, because there's somebody competent, somebody who uses a model already where they can incorporate this data and make some quantitative assessments about it, rather than other businesses and other users who might have a more ad hoc approach to using this kind of information.
Okay, thank you. Perhaps we didn't go into much detail in the way the project was set up, and it's not just SECLI-FIRM. There are a few others like that, which are based on case studies. And the case studies I mentioned in one example started because of a specific question from a user. So in actual fact, that's most of the work we did was driven by questions asked by users. So there was specific problems. We looked at specific seasons. But then obviously the problem is that we got the criticism that, you know, if you look at one season only, it's not going to tell you anything because it's probabilistic. So, you know, you have to balance a bit with looking at problem situations with, like Anka was saying, you know, then extend it and look at what happened in the past and try to see how, as many cases as possible, that you know, produce the forecast and how the situation, the result were. But I mean, related to this, actually, I wanted to touch on a question that something that I learned from you, Ayla, many years ago when you were working at Merrill Lynch. I remember you, one of your presentations here, you said that something that stuck around for a while, that it doesn't really matter what the skill of the forecast is, as long as you are the first to use it. So, I mean, to what extent having a forecast and being able to say, oh, I have a forecast and maybe I have it from the C3S or Met Office matters more than not having one, even if it's not always right.
Can I step in here? I remember a parallel conversation at a MetSoc. Well, it wasn't a Met Society meeting. It was a conference where we were discussing the results of a survey done by the Royal Meteorological Society. where somebody drew the conclusion that there were users who want to just know what forecast the competition bases their decision on. Doesn't matter if they're first or not. That they just
which
want
is
to
a similar thing, just to be first, get in first, and then
there's other angles to this.
Yes. So to what extent is having a forecast more important than having a skillful forecast?
I think having something to discuss around, it makes people think about the risk of the decisions they're making. So then they've got something that they didn't have before. So it was the total unknown. There's a certain amount of uncertainty around the result, but it gives you a starting point to discuss and assess the risk. So yeah, so it's right. Having something is definitely worth having.
Yes, yeah. So yeah, the parallel is always, if you don't have the forecast, you don't have anything, and so you flying in the dark, whereas at least you have something, and you can then say, okay, I use it or not use it. No. So I don't know, Jess, do you want to comment? Asking everybody.
Yeah, I'm not sure if I have too much to add. I guess, yeah, following on, even if I guess a forecast like the one we were producing for Shell, I guess it's an extra piece of information, which adds to maybe other forecasts that are out there, other bits of information that are being considered. So I think it adds value if there's I don't know. I think as a scientist, if there's no skill, I find it very hard to say that that's worth something just for saying you've got it. But yeah, even if it's not the most skillful thing, if sometimes it can add value to the user's decisions, then I think that's valuable.
We're in quite a unique position at National Grid. We're a monopoly. We're the only system operator. There is no competition. So from that side, we're trying to provide the best forecast for the market. We're not trying to beat anybody. In terms of having a forecast, really you just need to understand the variability. Even if you don't have a forecast, just how variable can this be? If you've got that, then essentially you're the first step towards having a forecast. And so that's where we always like to be. And then building on that and reducing that variability with forecasting.
Okay, thank you, Dan. And John.
You could add to that and say, what's better, one forecast or two? Do you have two that you argue about, or do you have one or nothing? But to answer your question, about 15 years ago, I was called up to see a VP. We had a rig stuck west of Ireland, had been there for about 3 months. And he said, when can I get this out? When can we get this 120 guys and girls on a platform back into shore? I said, well, there's a 1 in 10 chance that you'll get it out in January based on climatology. And if I had a forecast that was 3 or 4 weeks duration ahead, I would have seen a 10-day flat calm period in January west of Ireland. So yeah, a forecast would have been incredibly valuable then. So yeah, it's definitely better to have that rather than climatology or nothing.
Very good. No, keep it. Thanks, John. Yeah, we have a hand in the back. I can't quite see who that is. If you want to say your name, please.
Thank you. Thank you. Hi, I'm James Taylor. I think I have a couple of questions, and they're quite closely linked to previous questions or points. But my first is whether the forecasts are for, and they're sort of, my questions are really directed at Ian, but I'm also interested in the other applications as well. But are the forecasts for situational awareness, or are they actually directly for making a decision? And then sort of related to that, what sort of forecasts are useful? Are they probabilistic, or would a deterministic forecast do? And I think that's probably difficult to judge, because if it's all just for situational awareness, then it's sort of arm waving and you sort of, well, this is, but if it's actually directly for decision making, then you can sort of evaluate the worth of the forecast more easily and evaluate whether it's worth having probabilistic versus deterministic. But yeah, sorry, I should let you answer the question. But essentially, situational awareness was one issue, and the other is probabilistic forecasting. Those are the two things I'm interested in.
it's the forecast used for direct decision making, to answer the first question. So as well as planning production levels to meet customer demand, we also have to carry out maintenance activities. And this is very similar to John's case study, in that historically maintenance is being carried out in low demand periods, which would normally be March, April, and September, October, November, ahead of any cold weather in the winter or warm weather in the summer. Having the subseasonal forecast enables us to stretch those periods so that we can carry out maintenance activities that we wouldn't have in the past, especially things that are going to take 1 week or 2 weeks. We can have some confidence around using the subseasonal forecast that we can do maintenance activities that we wouldn't have done in the past. Whether the second part of the question, I don't really care. You know, whether it's probabilistic or as long as, you know, we've got some confidence and we build confidence around the service that we get and get confidence, we're already doing maintenance activities that we wouldn't have done at certain times of the year. We're taking advantage of the forecast, and that's going to make the company, you know, more profitable, and it will drive prices down, as Shanti said.
Excellent. Thank you, Ian. I don't know if other panel members, yeah, Dan?
Just on the probabilistic or deterministic. At the final point, when a decision needs to be made, we need a deterministic forecast, but that can be informed as you build up to that point by probabilistic forecasts that you then collapse down to a deterministic at the point of decision. So you're sort of hedging your position until you need to make that decision. So both is what we need.
Yeah, I'd say the same. We have traditionally relied on deterministic for the short term and ensembles for the next week to 10 days. But yeah, I agree. As long as you've got something that's seamless and continuous. Helps decisions.
Thanks. Yeah, and again, I think this is another point where, you know, deterministic and probabilistic, what we found is that you need to work with the people you're working with the users, or however you want to call them. And if they are stuck because the system doesn't allow to take probabilistic forecast, there's no point in forcing them to do so, because you just lose the conversation. And so that's what we ended up doing. We, like in SECLI-FIRM, we had to accept the fact from a scientific point of view may not be so a good point, you know, is not acceptable, but you need to get your hands dirty and do the work, and that will, in the longer run, things will improve. So that's what we found. We got going with this deterministic, and now the same people are talking about probabilistic because they understood that there is value into that. But it's yeah, it's a journey. Please, if you like to say your name, please.
Yes, David Warrilow. I'm sort of thinking this has all been very UK focused, and every country in the world has the same questions, I guess. So what I'd like to know is, how is it being done elsewhere? Where are the leaders in this kind of activity? Is it here, or is somewhere else jumped further ahead of us on this kind of activity?
Okay, Anka, yeah, want to? Thanks.
So in terms of seasonal forecast, virtually everybody around the world starts from the same data. The 8 systems I described earlier, maybe they're not all available, but certainly they cover. So everybody starts from the same place. Now, what they do and how they extract the information of relevance to the users from that data will obviously differ, because the uses are different. And that's why I hinted at about Australia. Not necessarily they have a better forecast system, but they have a better predictability, and certainly a better range of users who make decisions based on these things, because the predictability is higher, I suspect. So there they have developed methods of extracting the information that are much more sophisticated. In fact, they designed the forecast system to allow them to calibrate, to allow them to quantitatively modify the product, so they give people this thing. But it's not a fair comparison, because there things can be predicted. You can demonstrate skill. People would take the product and stick with it. So I think there is stuff to be learned from how other countries do things, but it's not going to give us ready-made answers. That's virtually. There's no need to worry, though, because the data is now exchanged sufficiently freely that effectively everybody works with from the same stuff.
Yeah. Yeah. I'll just give unless someone else, just give a quick, relatively quick answer to this. Let's say like Anka said, the problems are similar everywhere. The level of skill varies here and there, but the approach is the same. So in Europe, we are a little bit more advanced because the European Union decided to invest a lot. I mentioned about 25 projects, and there's no parallel in other continents. So we are fortunate in Europe for that reason. But at the same time, the approaches are very similar in all other places. And so, yeah, we can learn from each other, but I would say in Europe we've done most of the work, and that's why. And obviously here we are hosted by RioMetSoc, so there is a bit of more focus on UK. Okay, so is there any other? Okay, yeah. One last question.
I think earlier you said that there were something like 7 case studies in SECLI-FIRM, and I think we've mostly focused on maybe 2 of them. Do you want to just give us a brief overview of what the other case studies were?
Yes, I mean, actually there were 9, and in fact there were 12 because between, anyway, without complicating it, there's more than that. The brief answer is that all the case studies are represented and presented on the web. There is each case study has about 4 pages with a description of the problem, approach, and so on. So you can find a lot of information there. The other 2 major partners that were involved were Enel, electricity company in Italy. They played a major role in the project as partners. And one other was Alperia, which is a hydropower producer in north of Italy. And then we had also Tenet, the transmission operator. It was mentioned as part of case study 6, which is similar to Shell's case study 7. And then Thames Water and National Grid. So we had a variety of cases looking at hydropower generation, wind generation, demand, balancing demand and generation for in the energy space. So it was mainly energy, but with a little bit of water. Okay, so I think time is up now. I'd just like to give one very brief minute for anything you'd like to say, how you see the future of this we discussed, or anything you want to say, starting from Anka and then.
I've said already too much. I think the future's bright.
Okay, good. Thank you, Anka. That's positive. Yeah, we want to hear that.
Yeah, I'd like to come back in 2 years' time at the end of the project to take the service out to the other 9 water companies. Be interesting to see. It's been quite, having gone through the decision-making process and getting people on board and using the process. I've got to go and try and sell it to 9 other water companies. So I'll come back in 2 years' time and let you know how it gone.
Excellent. We'll wait for you, Ian and Jess.
Yeah, just to reiterate, I think there's some great work that's been started here. So it'll be really nice to see how that builds on in future. And yeah, be nice to follow the other work that's been going on in different industries too.
Thank you, Jess. Dan?
Just to keep working with us. We can't do this without the meteorologists. We just don't have the skills.
But you were a meteorologist. And very skilled. Yeah, collaboration. Yeah, sorry. Good.
Yeah, continue that collaboration and move it from oil and gas into the wind industry, where I think there are even more benefits.
Excellent. Thank you very much, all panelists and also known as speakers before. And thank you very much, the audience, for your questions, participation, organizers, RioMetSoc, and everybody who was involved in organization. Thanks again. Have a safe drive back home and see you soon.